Not everyone's online, you know. Okay. Problem with this one, or what's the issue? Should I use the other one? Yeah, the other one's better, I think. Okay, is this better? Online, everything is good too? Okay, let's get started. So we're almost at the middle of the semester, lecture 13. And today we're going to continue what we started, memory robustness, last time. I think I'm going to take the entire lecture to cover things that are building on robustness issues. So it'll be fun. At the end of the lecture, we're going to have some more fun on the review process. Why is this so slow? Okay, this way I can see my slides here also. Okay, cool. So just to jog your memory, we were talking about RowHammer. Everybody remembers RowHammer, right? Okay. And we discussed some security attacks. I gave you an example of the Google's attack, but there are many other attacks that we cannot cover in this course because there's a lot more other things to cover, other fundamental topics to cover, as we will go into. And there are security implications clearly, and people make jokes like this, if you remember. It's like RowHammer is like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door that you're actually after. And we talked about some papers, theses. I would recommend people to look at this particular thesis from GIRI. It's actually a very well done thesis on both developing experimental insights into RowHammer and row press phenomena, and also developing solutions to the problem. So GIRI introduced a block hammer solution we're going to talk about, for example. And deservedly, this thesis is one of the very few theses in the world that received awards from 3 different communities: computer architecture, computer microarchitecture, and also dependable systems. Okay, we did also spend some time understanding RowHammer last time, and we talked about the original RowHammer paper, which did a lot of analysis on understanding the characteristics of RowHammer. We're going to look a little bit more into those characteristics, but again, I'll point you to a lot of papers also, because there's more work in this area, and we also keep discovering new things. So it's a very fruitful area of research, also understanding what's going on with respect to RowHammer and other failure characteristics of real chips. We're going to focus a lot on DRAM, but other chips also, like flash, as we will talk about later, have similar characteristics. Also, processor chips. At the end of the lecture, we're going to mention logic errors. That's going to be important also. Okay, this was the infrastructure where I showed you results a lot from. And this was the infrastructure that we open sourced, and the DRAM vendor infrastructure. And again, we have a big laboratory. I just recently asked our admin to buy 25 more FPGAs with HBM so that we can expand this lab. I don't know if we will support the power delivery to that with many more FPGAs, but we will try our best. So that's the goal, basically, to discover new things that people don't know about in memory. It's fascinating that, as I mentioned last time, right, DRAM is a technology that's been around for 60 plus years. And even now, we're discovering a lot of things about it that no one has documented at the device level. I think this fascinates me. It's also good to think about the fact that we've scaled technology to very small dimensions. So there's some new effects that come up that no one has studied before. So maybe at larger dimensions, you don't have these effects as much, but as you scale memory technology or any technology to smaller dimensions, you get these effects that are very, like disturbance, for example, or other types of noise that need to be studied that have not been studied as much. So that's the part that's fascinating over here, I think. Well, one of the parts. Okay, we also discussed RowHammer solutions, at least the basic ones to begin with. Well, not necessarily basic ones, but first ones that are proposed. And we discussed that you need to protect the chips that are vulnerable in the field immediately. And you also need to have some longer term protection approaches. And this is also a very, let's say, fruitful area of research. People come up with new solutions So there's a lot of research that goes on in this area. And sometimes people come up with solutions that other people came up with, and they write papers in top conferences, but maybe they should be more careful in writing papers in top conferences, because the research record is something you cannot change, right? If the paper is there, and if someone repeats something very similar, and essentially if the claims are essentially the same, then you cannot change, right? You're obviously one of them must have come earlier. It's good to think about that. So my point is, whenever you're doing research, do a very extensive literature search. The first question that I ask my students, for example, when they develop an idea, one of the first questions is, has it been done? Right? Have you done the literature search to actually figure out that it was not done? It's a new idea, right? That's really important to think about. Okay, anyway, but there are a lot of new solutions also. Some of them make a lot of sense. Some of them are actually higher overhead. So we're going to talk about some of those as well. But we did talk about the para solution, for example, that we developed in our original paper, probabilistic adjacent row activation. And this was a very low overhead solution. And in our original paper, we thought that this was a good solution. And actually, the solution has good characteristics. But over time, as RowHammer vulnerability became much worse, this solution, even though it could still be used, it's still high overhead. Essentially, over time, with evidence, our thinking has changed, essentially, because, again, our goal as scientists is to collect evidence and to figure out whether something works still, right? And we think that para doesn't work as well anymore. But maybe there are ways of making it work. So these are some of the solution approaches that we discussed last time. We're going to get back to this. Especially, we're going to talk about some of the solutions that are employed in the field, but we're also going to talk about proactive throttling, like BlockHammer, as I mentioned. But we did dismiss some of these top solutions over here because they're either very expensive or not even secure. Like physical isolation is very hard to make secure, for example, or you need to make it extremely expensive by separating rows from each other as much as possible. Okay, in the end, solutions are always a trade-off between cost, power, performance, and complexity. So there are many dimensions over here. And also there's security over here. So does the solution allow some bit flips, for example? There could be solutions that don't allow any bit flips if they're correctly configured. But there could be more probabilistic solutions that allow some bit flips, but at a very low probability, right? As long as the probability is extremely low, based on some agreement, let's say, you basically, in the end, there's no solution that can completely guarantee things. But some solutions may fundamentally be probabilistic, right? The design of para, for example, is probabilistic. Based on some probability, you refresh the rows. It's not based on exact tracking of how many times you have activated this row. Right? So it's good to think about that, basically. Okay. So we also discussed last time state of the industry solutions, and we had a nice story, the real story, where industry claimed RowHammer is solved, and we basically said that, okay, maybe we should revisit RowHammer, and that's what we did toward the end of the lecture. We revisited RowHammer with this paper, we discussed it, and this paper actually changed the thinking in the field, showing that RowHammer is a very difficult problem to solve. It's a technology scaling problem, and to solve this, you really need to come up with a good solution, and we don't know what that solution is, basically. That's what this paper showed. And the main reason is, in the original paper, in the original RowHammer paper, you can see that you need to induce a bit flip, you need to activate a row by more than 130,000 times. But with our new scalability studies of many chips, almost 1,600 chips, we found out that some chips can get bit flips after 4,800 hammers. Okay, so we're actually marching closer to the HC first equals 1. Okay, you've also seen the slide, basically. This is kind of a history of what we have covered. Around 2018-19, there was a misconception, RowHammer is solved, and then we wrote this paper revisiting RowHammer, which showed that it's not solved. And then this led to other discoveries like RowPress, and also finally updating of the standards with PRAC, which we will talk a little bit more about per row activation counting. And then we'll talk a little bit more about some of these discoveries like variable retention, variable read disturbance, which is similar to variable retention time, which you have also seen in retention, and column disturbance. And we may actually have a session where we will talk about some of these cutting edge research. I'll not cover them, but we have not had a cutting edge research session where our students present some of the cutting edge work. So we will actually do that at some point, maybe sooner than later. Let's see. And there were many other works on understanding, solving, and exploiting RowHammer. And we're actually going to cover this side of the story right now, after 2020, what happened. So RowHammer research has kind of revived, which is good, I think. But industry always keeps claiming that there should be maybe less RowHammer research sometimes, which is very interesting too, because they always try to say, oh, our chips are less vulnerable because we have a lot of solutions. But this doesn't mean that it cannot be researched. Okay, this is a summary paper. You can read it actually on these slides. Okay, we also talked about the trespass paper, which also enabled the belief in the community to be changed in a different way, as opposed to understanding at the circuit level how the vulnerability is scaling. It looked at real DRAM chips, real DDR4 chips, and it basically said, can we actually hack them? Can we actually induce bit flips, even though there's some solution inside? And we discussed that. You were able to do that. You can see, I like this picture. You can do this with any solution to any problem, as you can see. If the solution is not good enough, you can bypass it, right? That's the key. And this is actually a nice picture because we are talking about robustness, right? Robustness is a very general problem in the end. We discussed last time that if you're sitting on this chair and chair is not robust, you may have issues. Yeah, if I'm standing on this floor and this floor is not robust, I may have issues, etc. So whenever we think about robustness, we need to think broadly to actually solve the problem actually. So if you actually have not a good solution like this, then it's easy for other people who are smart to bypass your solutions, right? Okay. And sometimes they bypass it even in a benign application, right? Meaning your solution doesn't take into account some factors, and as a result, you actually have bit flips because your solution thinks that RowHammer happens after 4,000, let's say, activations, but you actually have a mechanism where RowHammer happens after 50 activations. Right? So it's good to think about that. So basically, trespass showed that RowHammer is still an open problem, and security by obscurity is not a good solution in the end. Okay, so these two papers, especially revisiting RowHammer and trespass, led to a lot of discussions in industry, and industry actually immediately formed this task group in JEDEC, and they actually pushed out some of these papers. The system level RowHammer mitigation one essentially is almost like a similar solution direction like we proposed in revisiting RowHammer. So you need solutions at different levels, basically, because a single solution is unlikely to succeed all the time. And I actually agree with that. That's why we wrote in our 2020 paper. And more recently, industry introduced the per row activation counting, where in each row of a DRAM chip, an additional set of DRAM cells are added, and these DRAM cells track the number of activations that happen to that row. And for each row, you have this overhead, basically. Okay, we're going to talk more about that. We're going to see whether this proposal, as it's proposed, is actually good enough. And we're going to see that it's not necessarily that good. Okay, we're still discussing like what happened in the last lecture, but it's good to, I think, discuss that before we move on. And the last thing we discussed in the last lecture was uncovering target row refresh, which is the name of the solutions that are proposed by industry, umbrella name. That it's basically very poor. You can actually reverse engineer almost all of it if you actually spend some time on it. And if you actually have even more time, you can reverse engineer even more. And here we actually put different concepts that we have studied. We've used data retention failures as a side channel to detect whether a row is being refreshed internally by DRAM. And this is nice, actually. I like this sort of insight. This puts together data retention plus RowHammer. And it enables you a look inside the DRAM chip, even though you don't have a lot of control. Right? It enables you some observability because you measure the retention time of a row, and you think the retention time is low, meaning the row should lose its value, or at least some cells in the row should lose their values. But because you're also hammering, you crafted an access pattern that hammers DRAM. There's some internal mechanism that refreshes the row, and as a result, you're not going to lose the value at the refresh rate. And you can actually figure out that somebody internally refreshed it. You can figure out when did they refresh it. You can figure out how many times those refreshes happened because of the side channel, because you know the retention time of a row. Makes sense? And you can control the refresh rate. It's very simple things that you can control and you can measure, but it gives you a lot of insight into what's happening inside the DRAM chip. That's the fascinating part. And that's, in that sense, I think this paper is very, very innovative because it actually gave a much better methodology to understand what's going on inside the DRAM chip. And I think this sort of methodology can be used for other purposes as well. And maybe later we're going to discuss some other papers that try to glean what else is happening inside the DRAM chip. So it's good to think about these things, in my opinion. What other side channels exist that I can tap into to figure out what's going on inside the DRAM chip? Okay. And this paper also showed that basically, essentially, all of the chips that we tested are vulnerable, and ECC is actually a very poor mechanism because you need to actually have a very, very strong ECC, more ECC than a stronger ECC than what other prior work suggested. Okay, so there's more evidence building up against ECC, as you can see, right? But also, there's evidence that's good, but there's also a principled design, as we discussed, right? If you have a principled design, what is the goal of adding error correcting codes on all rows? The goal is to correct errors. And what kind of errors becomes the next question. These are errors. These ECC is very expensive mechanism because you add some redundancy so that if a bit flip happens here, the redundant data can enable you to fix the bit flip, right? Hamming codes, for example, or some other codes, Reed-Solomon codes, some other codes also. Apparently, some people in industry think that Reed-Solomon codes are not ECC, but you guys can. I'm not going to go into Reed-Solomon codes, but don't think that way. There are a lot of types of ECC in the world. But basically, if you add this ECC, you have some redundancy. And this is good for errors whose causes you cannot otherwise easily correct. For example, RowHammer is an error that we know, or failure mechanism, whose cause we know exactly, right? We know exactly why it's happening because you're hammering a row, right? So there should be better correction mechanisms than ECC. ECC may actually help, yes, but if you actually try to correct all of those, let's say 8 errors, 9 errors per code word, that's a lot of redundancy that you need to add. That's very expensive. Like, just to give you an idea, even detecting single errors, you actually need to add about 12.5% area cost to DRAM. That's what DRAM manufacturers did when they added ECC. They basically bit the bullet, and they added at least 12.5% additional area into DRAM, right? Am I right with the number? I think so, yeah. And if they want to actually increase that ECC, that number can easily go to 25%. And that eats away from the capacity of the chip. Right? And based on everything that we discussed, this is a very cost-sensitive area. And yeah. Another thing that's good to think about is, like, we talked a lot about processing in memory, processing using memory. It's good to think about how that interacts with ECC. So there, actually, it's good to think about, can you actually design ECC mechanisms that enable processing in memory or processing using memory work nicely? Okay, so that was kind of a summary of the last lecture. Any questions? Okay, now let's go into what else happened after 2020, 2021. I'm going to switch back to characterization and understanding, because in the end, it's really important to develop solutions, no question about that. Develop solutions that are secure, also efficient, low performance, low cost, low complexity. Ideally, we want all of that. But in order to develop those solutions, you really need to understand what's going on also. Because if you develop a solution without understanding, it may work well under some conditions, but you don't know under what conditions it's going to work, right? So you need to actually design your solution so that ideally you would like to understand everything possible that would affect the efficacy or effectiveness of a solution, and design the solution so that you don't have a security or bit flip problem under any condition. That's why understanding RowHammer is very important. And also by understanding, you can develop a solution that you could otherwise not think of, potentially, right? Yes? Well, depends, right? ECC could happen at the memory controller level. That's what happens in some systems. But these days, DRAM manufacturers are adding ECC inside the DRAM chip also. And those numbers, like 12.5%, were actually the changes made by the DRAM manufacturers to add ECC, single error correcting, or single error detecting, or single error correcting ECC inside the DRAM chips. Yeah, but you could also add it in the memory controller level, yes. But again, there's cost on the memory controller level too. Exactly, yeah. Yeah, you have a very good point. That's true. So you need to design mechanisms that work with processing using memory inside the DRAM chip. The question is, how do they work? So there's no, I think, very well accepted and known mechanism that works nicely with processing using memory. That's a great research topic. Any other questions? That was a very good one. Okay, so let's talk about new characteristics. So in this work, which is actually also in Micro 2021, together with Uncovering TRR, we wanted to look at different aspects of RowHammer that are not examined as much. And we looked at actually 3 things that affect bit flips: temperature, aggressor row active time, how long you keep the aggressor row open before you activate another row, or before you close the row and activate the same row, or activate the other row, which is on the other side of the victim, and the spatial location of the victim cell. And we find out that these parameters significantly affect when bit flips happen and how many bit flips happen. And if these affect things, now you need to develop solutions that take this into account, right? So the problem is actually more complex because temperature, row active time, and the location of the cell affects things. This could be used for, if you understand these things, you can also develop better attacks, right? It's actually a kind of a game, right? Attacker can do better if they understand what's going on in the chip, but the defender also can do better. So if you want to be a really good defender, you should always be ahead of the attacker. Right? It's good to think about that. Okay, so this is a summary of the work. I'm not going to go through all of the results because a lot of these papers have a lot of results, which is great, actually, from many chips. So in this case, we have results from more than 270 chips from 4 major manufacturers. There's a 4th manufacturer called Nanya, which we should test more and more, I think. That also has DRAM chips. It's not a major fraction of the market, but still they make chips. Some older chips, let's say, older technology chips. And we have a lot of takeaways. I'm going to give you 3 things over here. Basically, it turns out that RowHammer bit flip is more likely to occur in a bounded range of temperature. And that range depends on the cell. That's the interesting part. So for some cells, a temperature range of 50 to 60, let's say, degrees Celsius leads to the higher likelihood of bit flip. For some cells, that range is 20 to 30 degrees Celsius. For some cells, that's 80 to 90. And that's the highest likelihood for a given cell. So basically, there is no good relationship between temperature and at what temperature level a cell is affected badly, let's say. So this is still a bit puzzling because there are multiple different types of effects that happen at the device level that counteract each other. And as a result, you get this behavior where every cell is different, right? But this is actually also puzzling because now in order to actually figure out what's the worst condition for every cell or what's the worst condition globally, you need to test for a lot of temperatures. So testing actually becomes much worse. You cannot basically say at high temperatures, RowHammer is bad, so I'm going to test only high temperatures. There are some cells that actually fail much worse at low temperatures, right? So you need to test all of the temperature ranges. This is very different from retention errors, if you remember. Retention errors, it's a very well-known charge leakage mechanism, and charge leakage accelerates significantly with temperature. It's actually as an exponential relationship, right? Okay, so this makes life a bit harder for testing, as you can see. The second observation in this work, which led to another discovery, which is row press, which we will talk about, is a RowHammer bit flip actually is more likely to occur if the aggressor row is kept active for a longer time. You activate the aggressor row, you open the row, it's in the sense amplifiers, and you keep it active for some time before closing it and opening another aggressor row. And this is because there's a mechanism that accelerates charge leakage because of the passing gate, which we're not going to go into the lower levels, but I'm going to mention device level papers later on. And I have some slides at the end of this lecture that goes into device level observations, but we have a lot to cover. So you can take a look at those slides or read papers. And the third one is in certain physical regions of the DRAM module, you have a lot more bit flips, or a bit flip is more likely to occur. This is basically variation. This is due to the manufacturing variation. Some parts, some cells, or some physical regions are more vulnerable to RowHammer. Some physical regions are less vulnerable. And as I said, if you know which parts are vulnerable as an attacker, you can target those places, right? As a defender, you can protect those vulnerable places more than you protect other places. Then you can make your solution more efficient because you don't protect everything equally. Because if you protect everything equally, you should actually protect the worst case. Right? But if you protect based on the vulnerability level of every single cell or row, you can actually adapt the solution to the level of vulnerability. Okay, that's the idea, basically. I've given you a lot of these things, but let me give you one example. If you activate an aggressor row as frequently as possible, you get some HC first. And if you activate the aggressor row, if you keep the aggressor row active for a little bit longer, not terribly long, we're going to look at terribly long ones later, you get 36% reduction in the number of activations you need to do induce a bit flip. And essentially, if you configure your RowHammer solution to refresh adjacent rows, let's say, for example, with some HC first in mind, which is based on this sort of access pattern, now you're not going to cover, the solution will not cover this access pattern where you keep the row active a little bit longer. Because keeping the row active a little bit longer induces more disturbance, leading to a smaller HC first. So you need to be very careful how you configure your solution. And in order to configure your solution accurately, you need to take into account all possible access patterns. Right? Ideally, you would like to find the worst access pattern, right? And this is actually an open question right now. What is the worst access pattern to induce the bit flip as early as possible, or induce many bit flips? But this paper showed that there's another access pattern, keeping the row open a little bit longer, that is worse than what was discussed previously. Okay, this is another example over here. If you have variation across DRAM rows, and these are real numbers, basically 10% of the rows are twice as vulnerable than the remaining 90%, meaning the HC first of these 10% is half of the HC first of the remaining 90%. So if you know this, what you can do is you can target your mechanism, protection mechanism, such that it's much stronger. It takes faster action. For example, it refreshes earlier these rows, and it's less aggressive for the 90%. So your mechanism can be more efficient in terms of performance or area. Makes sense, right? Okay. An attacker can also leverage this clearly. I'm going to skip this temperature, but you can also, if the attacker, for example, or if the defender knows which temperature is worse, you can actually make your defense more efficient. Similarly, the attacker can actually try to attack at a higher temperature, or at the temperature that fits the cell. So there's a lot more in the paper. This is a very deep study, and you can look at Girai's presentation. This was part of Girai's thesis. Okay, if no questions, feel free to raise your hand if there are questions. Otherwise, I'll keep going. So there's more RowHammer analysis. Then the question is basically, under what other conditions RowHammer becomes more vulnerable, or can we actually fix it if we understand things more? So this is another study that Girai actually did, which was published at DSN. And the idea is to check, to figure out the relationship between the word line voltage, the voltage level at which you activate a row, essentially, and the RowHammer vulnerability. So intuitively, well, again, for this, the infrastructure needs to be extended so that you can measure voltage nicely, or you can you can modulate voltage effectively. And basically, intuitively, what you would expect is if the voltage level that you apply to a word line is high, intuitively, you should cause more disturbance, right? Because you have a lot of voltage level, and that should actually affect cells around you more. If the voltage level is low, you should get less disturbance. And that's what we observe, actually. So basically, that's the good part, essentially. Again, with more than 270 chips, we find out that reducing the word line voltage, the activation voltage, essentially, reduces the bit error rate of a RowHammer attack or RowHammer access pattern that's bad significantly, which is good. But it also has other effects that we don't want. Reducing the voltage level also reduces how fast you activate things, right? Because at low voltage, you're operating slowly. And as a result, this increases your row activation latency. And you can see, again, there's a lot of data in the paper. It also reduces data retention time, again, for the same reason, basically. Low voltage, you're more vulnerable to leakage. And you can see that you can actually, the paper proposes some mechanisms to actually overcome some of these issues. Like if the row activation latency increases, you can reliably operate by increasing the latency for some rows that are affected, right? You reduce the voltage level, but for some rows that are affected, because now you need to access them longer, you increase the access latency. For some rows that are affected, because you reduce the voltage level and your data retention time reduces, you add more ECC, for example, or double the refresh rate. So you can have solutions to this, and you can come up with a mechanism that reduces the RowHammer vulnerability without significantly affecting reliable DRAM operation. But this is very difficult to do because now you actually need to take into account all of these effects, and you need to make sure that all of these actually work under all possible conditions, right? So in the end, I think this is a very good study, but it's very hard to reduce. And this is a study that needs to be done. This is science, right? We really need to understand what's going on. And the conclusion of this study is it's possible to have a less RowHammer vulnerable system with the reduced line voltage, but it comes with a lot of costs. You need to take into account all of the other effects. Make sense? Okay. So later, which I'm not going to go into, we have also looked at RowHammer and HBM, high bandwidth memory chips, which are probably but GPUs use a lot of HBM heavily these days because they have high bandwidth, and GPUs require high bandwidth, both because they're highly parallel and also the applications that are run on GPUs today, the common applications, which is machine learning, requires very high memory bandwidth and also memory capacity. And we show that actually GPUs are also, not GPUs, HBM chips are also very vulnerable to RowHammer. It's very similar essentially to DDR4. And the main reason is the internal array, subarray in an HBM chip is very, very similar. It's essentially the same thing as the internal array, subarray that you use inside a DDR4 chip. What's different is the interface, so that you can get much higher bandwidth interface, and it becomes very expensive also because of that higher bandwidth. We have discussed this very early on in these lectures. And what's different is the outsides, like peripheral circuitry to support that interface. It's really not the, and also the HBM has like 2.5D or 3D stacking, where you have mechanisms to actually get data out quickly because of that stacking. So basically the vulnerability of HBM is very similar. There are some other things that this paper examines that are HBM specific, but I don't want to go into that. It's not, let's say, first order. What do you think, Smile? Am I correct? Okay, yeah. But maybe people will figure out that future chips that are more tightly integrated in a 3D manner, there are different kinds of, or maybe RowHammer becomes worse or better. It's good. It remains to be seen, basically. The difficulty is this sort of infrastructure is very, very hard to build. Today, for example, we have HBM2. HBM3, it's very difficult to get in academia because there's a huge demand from industry to actually buy HBM chips, right? HBM3. And there's the supply is very small. That's one of the reasons why HBM is very expensive. The demand is very high, supply is very low. And basic economics dictates that the price goes high, right? If you guys have studied macroeconomics, you would know that. And also, it's also hard to manufacture HBM because it's very high bandwidth, right? There are two reasons why it's expensive, because the bandwidth is very high, and we already discussed that you can get high bandwidth by making things more expensive. You basically have a lot more, either very high frequency, a lot more pins, and a lot more, let's say, wires, and that actually makes things expensive. Okay, anyway, I just want to take a detour over here, but these sort of studies are really important going into the future. Okay, so Giray did more work on analyzing spatial variation, and he actually went into things a little bit more deeper in this paper, where he looked at the characteristics of spatial variation across many chips. Again, I will not talk about this in detail, but this paper proposes, examines a lot of data on which parts of a DRAM chip are actually more vulnerable and why, as much as possible. And can you actually design a scalable solution at the memory controller level to detect those parts and protect them more or less, depending on the vulnerability level. So that's a very deep study on spatial variation. So it's good to think about that again. This is, in my opinion, these are groundbreaking works that actually figure out what's going on inside the DRAM chip. We're going to talk about the temporal variation also. So spatially, vulnerability varies, but temporally does it vary also. Spatial means different cells have different vulnerability, okay? There's a good reason for it, manufacturing variation, right? We know that different cells are different. You know that from retention time, for example. But temporally, is there a variation also? Temporally meaning a single cell has different vulnerability at different times. So we talked about variable retention time and retention time. That's a temporal variation example, right? And it turns out there's a similar effect that exists, and Altaberg studied it in HPCA this year in 2025. It's called variable read disturbance. I'm going to mention that, but again, we're not going to go into that in detail. Okay, before we go into more studies, let's talk about like new attacks and solutions. While people were doing studies on figuring out what's going on inside the DRAM chip, is the vulnerability affected under different conditions, under different cells, etc. There were also a lot of people who were developing new attacks. I cannot cover the space here because there's a lot, and also new solutions. I'm going to mention a couple of things that are really interesting. This is really interesting, I think, because Google was working on this problem for a long time, starting from their Google Project Zero paper, not paper, but Black Hat presentation, where they showed that they could take over a system, right? And they did more studies internally to understand this effect. And in this case, in this work, they introduced this half-double attack. It's very interesting because they tried to examine a mechanism where you don't have a single aggressor row. This is what classic RowHammer, as they call it, right? You have a single aggressor row. You can have double aggressors, but that's okay. Forget about the double-sided RowHammer for now. You can still have double-sided over here, but let's look at the single-sided. You have one aggressor over here. You hammer it a lot, many times. And then you hammer aggressor B a little bit, maybe 100 times. It turns out you get bit flips in this victim that's closer to aggressor that you hammered little. They showed that this is actually possible in real DRAM chips. This is interesting because now you have one aggressor and another aggressor affecting, let's call this the far aggressor. This is a near aggressor. A far aggressor does a lot of hammering, near aggressor does a little bit hammering, and the victim gets a bit flip. This was not demonstrated before. So that's why it's interesting. They called it half double. I don't remember why they called it half double, but they called it half double. Anyway, but basically, the implication of this is you need their access. This is another access pattern that induced a bit flip in a way that you may not predict, right? So if you actually were looking at only this access pattern, you would configure your RowHammer defense such that you basically assume an HC first that's large. But now, even though this HC first may be somewhat large, smaller than this one actually, you can actually get a bit flip. Now, what's worse? Maybe you kind of can avoid that. What's worse is if you actually have a defense mechanism that detects this aggressor, it would refresh aggressor B, right? And your defense mechanism can become an attack. Make sense? Because now aggressor A is activated many times, and that activation caused the defense mechanism to refresh aggressor B, which means aggressor B is actually activated many times, maybe not as many times as aggressor A, but enough times that you could induce a bit flip in victim C. So I think that's the real interesting thing in this work that shows that a defense mechanism itself can become an attack because of the underlying issues of how RowHammer happens. That sounds pretty interesting, right? Okay, so this is interesting, and you can read the paper. They first put out a blog post, and then they wrote a paper about this, showing that they could actually launch these attacks in real DRAM chips. Okay. At the same time, Microsoft was also doing a lot of research in this area. They were publishing papers, including some papers with us. But basically, this work was one of the interesting works that they published. I will not go into a lot of detail over here, but this work basically showed that you can do hammering that induces coherence actions, and coherence we're going to cover later on. But coherence is to keep caches coherent, meaning consistent with each other. The same data has the same value, same address has the same value when they're cached. But you can induce coherence actions by doing a lot of hammering. And these coherence actions actually can lead to bit flips in commodity workloads. So they actually show that some commodity workloads can do activations that exceed the RowHammer vulnerability on some chips. So non-malicious code can actually do this. So in hindsight, this turns out to be very similar to how Intel got to know about RowHammer originally. where someone said, oh, we have this workload where we get bit flips. And the poor Intel engineer, if you remember from the last lecture, had to spend a year to figure out why this bit flip is happening. And they eventually figured out it's not because of Intel's problem, it's because of RowHammer, essentially. Something's happening inside the DRAM chip. So it turns out what is documented by Microsoft is very similar to how originally these bit flips were discovered or communicated to Intel, except it happens 12 years later. So you can see the interesting thing over here, right? It would have been nicer if Intel wrote a paper documenting it, but I don't think they wanted the heat. Okay, let's talk about solutions also. This solution I mentioned multiple times. I will not go into a lot of detail, but this is a solution that's different from what was proposed in the earlier approaches. So we discussed that you can do a proactive reactive refresh, right? You try to detect which rows are activated a lot. And if a row is activated more than some threshold, you refresh adjacent rows. You can refresh one adjacent row on each side or two adjacent rows or three adjacent rows, depending on your comfort level. So if you can also detect how many times a row is activated before you get bit flips, you can stop access to that row. Right? That's the idea over here. You can block access to the row before bit flips happen. So how do you make it work is the key question over here. So why is this interesting? Basically, it's interesting because you want a scalable solution as RowHammer vulnerability becomes worse. And ideally, assuming you're ideally from the perspective of a processor manufacturer that doesn't trust DRAM, for example, you want a commodity DRAM chip and you don't want any modifications to the chip or the interface. Right? So this solution can be completely implemented in the DRAM controller because you don't need to know anything about the DRAM chip. You just need to know the vulnerability, of course. That you need to know. I think all of the solutions need to know the vulnerability level. So basically, the idea is there's some RowHammer that's happening to repeatedly accessing row A. And BlockHammer solution uses area-efficient Bloom filters. Remember the Bloom filters from the Radar work? It's very similar, except it's a little bit more complicated Bloom filter, but basic idea is very similar. It uses Bloom filters to detect that a row is activated too many times, let's say, based on a threshold, and it selectively throttles accesses to that row. That's the idea. It stops accesses. So in the memory controller, you can completely implement it. And you can actually figure out how to do this such that bit flips do not occur. Of course, you need to know how many times a row can be activated. And if you do this, you can also optionally inform the system software about the attack. We actually had a RowHammer likelihood index that we introduced in this paper, which is an index that quite accurately predicts whether a RowHammer attack is going on. Okay, that's the idea. Implementation requires more work. So how do you actually design the Bloom filters? How do you clear them becomes important, because one of the issues with Bloom filters that you very well know based on what we have discussed in Radar refreshes, once you insert something into a Bloom filter, you cannot remove it selectively. Right? So you need to clear the Bloom filter once in a while. For this, you have double Bloom filters, but I'm not going to go into the details of implementation. And also another issue with the Bloom filter is you can get false positives, right? So you may actually throttle a row or block a row for some time because some other row's address maps to the same Bloom filter. And that other row is being attacked, but not this row that you're trying to access. So there are issues with the solution also, but this is a solution that could work. It turns out it's scalable, but it's not as scalable as the RowHammer vulnerability goes down to, let's say, 100 or 64. So maybe 1,000 is okay. This paper shows that 1,000 activations is okay, but beyond 1,000 is not easy. So there's more work that needs to be done in this area. But one of the benefits of the solution is it's compatible with commodity DRAM chips. There's no need for proprietary info or modifications to DRAM chips. If you think about PARA, for example, probabilistic adjacent row activation, that requires information from the DRAM chip because it requires refreshing the adjacent rows. And that information is not available to the memory controller. The memory controller doesn't know which rows are adjacent. This particular solution doesn't require that information, right? Because you're throttling the row that you're accessing too much or too many times. Okay, this also we also released a lot of RowHammer solutions with this BlockHammer paper. So if you're interested, I recommend looking at the paper because it covers a lot of the solutions that have been done until 2021. It categorizes them also. So, but this is an example of another intelligent controller, right? Now you have even more intelligent controller that keeps track of things. Yes. So overhead of so TRR depends on what TRR means, basically. So there's no single definition of TRR, target row refresh. But the overhead is lower. If, for example, if you want to keep track of n rows, n is a relatively large number, assume. BlockHammer's overhead is much lower, because if you want to do that, I will rephrase your question. Is the overhead lower than exactly tracking rows? Absolutely yes. Because if you want to keep track of rows, exact activation counts of each row, then what you need is really a content addressable memory, and it's expensive, basically. Or some sort of associative structure in the end, because direct map doesn't work very well in that case. But basically, the overhead is expensive, and the BlockHammer paper shows that. So it's cheaper. The trade-off is basically you don't keep track of rows exactly, but you get false positives.
But a solution like TRR can also be
Exactly, yeah. So there could be things in in the middle. So it's good to think about that. Yes.
In that case, what else would be
Maybe, yeah, yeah. Are there works that implement use Bloom filters? I guess there are. Yes. Comet is one. Not exactly Bloom filters, but hash-based counter. Yeah. So we should talk to Nisa over here. I like the idea of using Bloom filters, actually. There should be a better mechanism, in my opinion, at some point. But the issue is, like, this sort of solution is good at very high, not very high, relatively high HC first. Once you go into HC first of, let's say, 256, 128, 150, the Bloom filters need to be large. You get a lot more false positives, etc. So you need to actually think a little bit more differently. So those low thresholds are actually very difficult to handle.
so in that case, maybe we would require multiple.
Maybe, yeah. But multiple Bloom filters have become hard to manage also. So that's good. You're brainstorming. Yeah, you should definitely take a, I'm going to mention some of these other works. Like, you should definitely talk to Nisa, Ataberk, Ismail over here. There could be better solutions. There are always new solutions that are submitted to top conferences, actually. Some of them repeat the old solutions, but don't do that. Yeah. Okay, anyway. Okay, these are the solution approaches. There's another solution approach that's not in this picture, which is remapping the rows. We actually looked at the solution approach in the Crow paper that you have seen in the latency. So one idea is basically, if you detect a row is activate a lot, you figure this out, move that row somewhere else. Right? Now it can disturb other rows, and hopefully not the rows that are almost going to get this corrupted. I think this is an interesting idea, technically, but if you think about it, what is the benefit of this, right? I feel, as a principle, then the question is, do you really want to move the row somewhere else, or you want to refresh the adjacent rows? It's good to think about that. So if you move the row somewhere else, then you get some benefit. You don't need to know which rows are adjacent to you. That's the good part. So there's some benefit to this idea. But moving the row somewhere else takes a lot of data movement, right? So it's good to think about that, right? So fundamentally, it's a different approach. It can also be agnostic of the DRAM chip's internals. That's the advantage. But moving the row somewhere else is actually something that we want to reduce as much as possible based on the lectures on processing in memory, right? We don't want to incur more data movement. We want to incur less data movement as much as possible. But there are works in that direction. Some of them actually add DRAM support, internal DRAM support, so that you can actually do this data row movement relatively quickly internally inside the subarray, building on ideas like row clone, for example. Okay, so there's another approach over here, basically, that's not on the slides. Okay, so industry finally actually added these per row activation counters, as we discussed. And you can read this paper. It's a 2-page paper that discusses RowHammer. And interestingly, it doesn't cite our original RowHammer paper. It cites the revisiting RowHammer paper. I don't know why. But anyway, well, this is a solution in a right direction, in my opinion, because they're trying to solve the problem in a better way than what they did before. The difficulty is now you have more overhead inside the DRAM chip. So every cell or every row has some metadata, some other DRAM cells that actually keep track of the activations, right? How many activation counts, how many activations happen, basically. in that row. And there's some logic internally to figure out when you should take action, right? And they don't discuss all of these details, of course. It's still security by obscurity. But the good news is there's something being done. And so that's one approach. This is one that's standardized. Samsung also had a paper that is very hard to parse, so I'm not going to go into the details, but there are some ideas over here, but it's not as secure. Google later showed that the solution is not secure, so you can ignore it. Okay. Microsoft actually had a paper that is kind of the precursor to this per row hammer tracking that Hynix called. They basically talk about per row activation counters internally and how to manage them, etc. You can take a look at that. This is not a full paper. It's a DRAM sec paper. So there are some evaluations that haven't been done as much over here, but you can take a look at it. It's an early precursor. So this was an idea, as I said, in our original paper we considered, but we thought it was not a good solution because we thought it was expensive. We wanted to develop a cheap solution, right? Which was Para, which I think is cheap. But I think this idea is what we considered, but it's still not a great solution in my opinion, but it's a solution in the right direction because it makes things better. Okay, so this solution was actually standardized in JEDEC as per row activation counters. But of course, you should always ask the question, are these solutions good? Right? And it turns out you need to configure these solutions very, very carefully again. Right? So configuration becomes a problem, basically. How do you, we don't know enough information as to how this is implemented or how this is going to be implemented in real DRAM chips, right? There are a lot of questions over here. How do you configure? What is the HC first internally? When does okay, you increment the counters. You can have a lot of mechanisms to increment the counters. How do you increment the counters? How do you ensure that you actually take the mitigating action at the right time? What is that value? How is this configured? There are a lot of open questions over here, basically. And it turns out we analyzed this in a DRAM sec paper, which later got extended to this HPCA work. And we basically showed that it's not easy to configure. And if you configure things to be safe, the overheads may increase. Let me quickly talk about what industry exactly implement. Not exactly, but what industry is thinking about implementing, and they've implemented some of the chips. And the idea is the DRAM chip tracks row activations. And because the DRAM chip cannot, internally it does something, but at some point it may get overwhelmed, right? It may actually have a lot of things that it needs to refresh. And internally, the DRAM chip figures this out and says, help. There's actually an alert signal in DDR5 or DDR, which is basically reserved for very bad cases. Maybe there's some error in the DRAM chip. It says basically you raise an alert signal and the memory controller is supposed to say, oh, the DRAM chip is in trouble. Let me do something, right? So this heavy-handed solution is adopted in PI. So because internally, memory controller, okay, DRAM chip and memory controller are in a very asymmetric position, right? Memory controller has all the power, DRAM chip has no power in the sense that it cannot make decisions by itself. The memory controller sends commands, it keeps sending activations. Internally, DRAM chip says, oh, okay, I need to refresh these rows, but I don't have time. And if it figures out that it doesn't have enough time, it raises alert signal. There's something seriously wrong. And the memory controller at that point stops. Right. That's the idea. It requests RFMs. How do they handle the difference between an alert for some other reason and an alert for this reason? So there's some magic over there. Yeah, basically alert can happen because of multiple reasons, but we don't know how they handle the difference yet. Okay, so basically you have these counters and you track the aggressor row activations. There's also another issue over here. You need to make sure that the counters don't get corrupted, right? Right, because you keep activating counters also. But I think that could be solved by aggregating the counts in a less frequent manner than the number of activations potentially. It can be stored somewhere else, but yeah, okay. There are a lot of implementation issues here, as you can see, right? Because the counters are the watchers. Who watches the watcher, right? Yes, okay.
What's the charge over time?
Yeah. Yeah, basically we don't know as much. That's something that we cannot measure as well. That's something that people model in TCAD, but it's not linear for sure. Yeah. That we know for sure, but it's very hard to model. And it's dependent on which cell as well. Okay, so basically, this allows accurate tracking of regressor row activations, and you keep tracking. And it turns out one of the other issues is basically you need to count the DRAM, how many times you activate, and when do you actually update this counter, right? The way it's proposed in the standard is you you increment the counter when the row is being closed. And in this paper, we argue that this is a bad idea, essentially, because it increases your pre-charge latency by 140% in one data sheet, for example. These are from real data sheets. Some latencies increase, some latencies reduce because they do some other optimizations internally. But in the paper, we show that this actually reduces your performance significantly in some conditions when you have a high memory intensity. Make sense? So basically, how do you implement a solution like this becomes an issue. I think because they didn't want to change DRAM significantly, they decided, oh, we're going to increment these counters by adding a little bit more to the latency of a pre-charge operation. It's okay if you're not doing a lot of pre-charges, but if your program is doing a lot of pre-charges now, it gets affected significantly. And this happens under heavy conditions where you have a lot of accesses to memory and you have a lot of bank conflicts, right? So this paper actually is one of the first to quantify that, and later papers actually showed that as well. So one of the issues is basically what happens if the DRAM chip gets overwhelmed, and basically it says back off, which is the alert signal, very heavy-handed. And at that point, basically, I will not go into a lot of detail because there's a lot of detail over here, but CPU actually takes over and essentially sends some RFMs, refresh management commands, to have the DRAM chip refresh itself internally. So it cannot do any other activates at that point. And that interval can be very long, right? Was it 1400 nanoseconds? Yeah, 1400 nanoseconds is a long time. Basically, don't get the DRAM chip overwhelmed. So DRAM chip can get overwhelmed if you activate the HC first is low. Right. So this paper shows that if your HC first is low, you get significant performance degradation, essentially. And again, you can read the paper for more detail, but this is a summary. It poorly scales the DRAM chips because you have some adversarial access pattern that can actually induce these alerts or backoffs, as they call it, more frequently than a not adversarial pattern would. Again, you can read the paper, but you can see that there's a significant performance overhead for existing chips, like 6%, because you need additional time to track read disturbance aggressors. That's a normal operation, because they always increase this pre-charge latency. And if you have a future chip, it's vulnerable, so you need to be careful about what you do. And this paper proposed some solution, but I'm not going to talk about the solutions. You can read this paper, and maybe this will be presented as part of the cutting-edge research. Okay, and we show that this outperforms existing solutions. So Cronus is an existing solution that is better than prior solutions. I should also tell a story about this paper. This paper, it turns out we had a bug in the simulator, and some of in the configuration of our simulator in this paper. And we got notified by some authors who wrote a paper related to this. And we found out that we were not changing some of the parameters accurately. And the first thing we did is, of course, fix the bug, right? That's the right thing to do. So we fixed the bug. We reran the results. Results are slightly different, but it doesn't change the major conclusions of the paper. So for example, the significant performance overhead was 10%, now it's 6%. There's some difference, as you can see, because of the bug. And we actually updated the archive version of the paper with updated results. You can read the Appendix E of the archive version to see what is different. And we actually document what is different from the original paper. So it's a good example of, in my opinion, how to actually revise the research, right? There will always be bugs, no question about that. Bugs are there, and even in commercial software, right? And in the end, if a bug is discovered, you need to adapt accordingly. You need to do the right thing, which is really changing the results and actually updating the paper. Makes sense. And I think publication mechanisms like archive are really good for this purpose, because that's how a paper is live, right? I tell my students, a paper never ends. It's a living thing. There's pre-publication, There's during publication, meaning you need to prepare the thing that gets exposed to the world. And then there's post-publication, which is it's exposed to the world and it lives its life after that. A lot of papers die after they're exposed because they're very incremental and not so interesting, let's say, especially these days. But some papers live for many years, and some papers also need to be adapted. They need to change, right? It's always good to have a chance to update the works. Okay, so the question is always, can we do better, right? Now I'm going to give you another mechanism called self-managing DRAM. It's actually not a mechanism, but a principled approach of designing the interface between DRAM and the memory controller that actually makes a lot of things much easier and better. It's a more memory-centric interface, essentially. So we saw, for example, with this Chronos, that the memory controller does everything, right? Memory controller sends the refresh commands, activates internally, DRAM chip does some counting, but at some point, if the DRAM chip cannot do a mitigating action, it takes a very heavy-handed approach, says, memory controller, I'm dying. Alert. That's alert means that basically. Something is seriously wrong. This is because we don't have a very good interface between the memory controller and the DRAM chip. Memory controller needs to decide everything. And then when the memory controller somehow figures out that it's dying because internally the counters, internally some things need to be refreshed, the memory controller says, okay, now you can do refreshes. It's a very bad way of designing the interface if you think about it. So in this paper, we basically, this is Micro 2024. This is after JEDEC update to the standard, but I'll have a story about that soon. Basically, the thing that we propose is a much better way of designing the interface, in our opinion. In fact, actually, it's evidence. We have a lot of evidence for this. And the idea is to enable the DRAM chip to control its own maintenance operations without involving the memory controller. Basically, the DRAM chip should not tell the memory controller that, oh, I'm dying, right? I need to do something. The DRAM chip internally does its refresh operations while the memory controller is trying to access. And if the DRAM chip is doing some operation in an area where the memory controller is trying to access, memory controller DRAM chip says, no, try again, right? It's kind of similar to the interactions that we have, for example, right? If I'm busy, I tell you, try again, right? That's how it works. So basically, that's the idea over here. DRAM chip is responsible for maintenance operations, and we design an interface that in a nice way, such that we can change the maintenance operations inside the DRAM chip as we want, without changing the memory controller or changing the interface again. That's the idea. This way, memory controller can do things what it's good at, which is really scheduling access operations, for example, but it doesn't deal with things like refresh. It doesn't need to basically keep sending commands, refresh, 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 refresh. It doesn't, and the DRAM chip doesn't get overwhelmed. It doesn't need to say, I'm dying, right? Alert, basically. That's the idea over here. And also, DRAM manufacturers know a lot about their DRAM chips. They can optimize refresh. They can optimize RowHammer protection. They can optimize scrubbing, etc. So this is the basically key idea. How do you enable DRAM chip to control its own operations? You need to change the interface once. And the idea over here is to have an interface that says, that gives a negative acknowledgement. For example, whenever the memory controller activates a row, the DRAM chip says, no, I cannot activate that row because at that particular part of DRAM that you're trying to activate right now, I'm doing something important, meaning I'm doing RowHammer protection in that area, for example. It could be refresh. So that's the idea, basically. This way, again, we partition the work nicely. In our opinion, this is much nicer than the current partition. And this way, you don't need to say, I'm dying. It basically says you reject and activate. It's only one activate command you reject. And the memory controller doesn't need to do anything else other than retrying that activate some other time. And it can actually induce bounds as to when the memory controller needs to retry. There could be standards that specify that, essentially. And in this paper, we showed that you can implement both fixed rate refresh, periodic refresh, as well as variable rate refresh, like Raider type of mechanism inside the DRAM chip very nicely, cleanly, without changing the interface. You can implement different types of RowHammer protection mechanisms. You can implement memory scrubbing mechanisms. So this interface is actually, I think, a step in the right direction. It's not adopted yet, but it's much better than this alert signal, which is being abused today, actually. Because alert has a very specific function, right? If the memory chip is really dying, it cannot work, for example, for some reason. you raise the alert. And if you actually start overloading the alert signal, oh, memory chip needs time, so let's overload the signal, then actually the interface is broken. Well, it's already broken, but you're really trying to work with a broken interface as opposed to fixing the real problem. Okay, so this is self-managing DRAM. Maybe not so surprisingly, this was rejected 6 times by the community. So we had this work relatively early, before JEDEC actually released their standard, but we published it after JEDEC released their standard, thanks to our reviewers. Let me give you one of the major reasons why this was rejected is, what are some business impediments of this approach? These are real reviews that we received from reviewers. The idea is commercially unattractive. Do I care? Maybe it's unattractive right now and to you, but maybe our goal is something bigger, right? Okay, I'm gonna skip some of these things. It requires changes to the DRAM interface. Okay, that sounds bad, right? It's working okay, why change, right? It's an interesting mindset. So you can see strength is radical idea, advocating for industrial shift on features generally relegated to processor-side memory controller. This is a real review again. I disagree that this is a radical idea, by the way. I can imagine many, many other radical ideas that one could come up with. It's just a simple move in the right direction, I would say. But the weakness and the reason for rejection is complex and requires co-design, likely will remain as an academic work, which is not necessarily a bad thing, assuming it inspires other things, right? So there's a mindset problem, as you can see. Are the reviewers asking the right questions? As a result, this paper was rejected 6 times. But there are also research-oriented reviewers exist, basically. This is a good idea and good way to introduce a layer of abstraction between DRAM and memory control. I agree with this, actually. There are some practical problems, like with every idea, for sure. But this reviewer is nice. These are not fundamental. So this paper was accepted after 3.5 years after the research is done. And with every iteration, not too much has changed, let's say. The basic idea remained the same. So it's good to think about that. So you can see some window into how academic research is done. And it's not clear if these are how reviews should be, right? So basically my takeaway is that if you want to solve fundamental problems, you should not think about the business as usual. Right? If your goal is to get things implemented right away, that should not be the goal in research. Maybe some research does it, that's fine. I think we should be accepting all kinds of diverse methods of research, but not all research has to be implemented right away, right? Then it's not research anymore, that's implementation. Okay, so it's good to ask the question we have asked multiple times. What would a smart 10-year-old kid do if they don't actually have this baggage of industry and making a lot of money in industry? They will think a little bit more, a little bit better. Okay, so I think standards, so this is actually a problem with the standards, meaning there's an interface that's defined between processor and memory. And if you deviate from that interface a little bit, it hurts some people for some reason. I don't understand why, but in research, basically, we should be open to many ideas, right? But as you can see, this idea, for some reason, was seen as radical. But I think you should not be shackled by standards and reviewers. There's a right thing to do, and there's something comment you get. So you need to be resilient, basically. I think in the end, innovation is not an easy thing, but it actually gets slowed down because of these standards and reviewers. We should really be breaking some of the standards to actually move. But for researchers, if you're a researcher, I guarantee you that you will get comments like this at some point. Or if you're a forward thinker, actually, not just a researcher in general, you will get comments like this. And being resilient is really important. And you got to push back, basically, because many people, especially if they're set in their ways of doing things, the first reaction will be, I'm not going to change. The 10th reaction may be also that. But if there is a good idea, at some point it will prevail. You don't guarantee when it will prevail, but it can prevail. Okay, this is a good place to take a break, I think. We're going to have more of this discussion, actually, for reviews. But I wanted to discuss this because this SMD idea, I think, is a very nice way of, principled way of designing the interface. Because the principle is basically, the principle is basically very simple. There are multiple principles. The memory controller should do what it's good at. The DRAM chip should do what it's good at. And the interface should minimally be changed to allow those two functions. That's the idea. And that's the principle. And this principle apparently disturbs a lot of people. We can talk about why later, but let's take a break right now. So let's take a break until 2:40, so about 15 minutes, and then we will continue. Okay. Well, I think it's time. Yeah. Okay, so we covered some solutions and a principled solution of designing the interface. I think this sort of interface can enable other solutions. But now let's go back to understanding and asking the question, are we RowHammer free? Even if you have very principled solutions and good solutions. And maybe the broader question is, are we free of these bit flips, right? And basically, this is the question we asked in some of our works around 2021, 2022, etc. And the question was, what if there is another bit flip phenomenon, not necessarily exactly RowHammer, that doesn't require a high activation count? All of these solutions are designed for some activation count. If there's another phenomenon that actually reduces that activation count to induce a bit flip, these solutions will not work very well. And this is what we discovered and published at ISCA 2023. Basically, until 2020, RowHammer was the only known read disturbance bit flip mechanism that affects real commodity DRAM chips until RowPress. So I'm going to talk about RowPress now, which is a fascinating thing. I think this is Hao Song's master's thesis. He should have gotten the ETH medal for this also, but ETH decided they didn't want. I don't know what's wrong with ETH, sorry. but this is definitely award-winning, medal-winning work, in my opinion. Yeah, I don't know, maybe sometimes the CS department thinks that hardware is not computer science or something. I don't know. You can ask them. But this is really fundamental work, and it's really a discovery of a different bit flip mechanism that was not known or documented at the device level. Later, people at the device level wrote papers describing how this mechanism works and how this happens. They modeled it. And I have some device level slides at the backup slides if you're interested in exactly how this works, what electrons get attracted, etc. But again, I'm not going to go to that level. So what is the problem, basically? The high-level summary of the paper is this. It demonstrates and analyzes for the first time a new read disturbance phenomenon that causes bit flips in real DRAM chips. And it demonstrates definitively that this is different from RowHammer. Basically, this is not RowHammer. This is also not retention bit flips. That's kind of obvious, but we need to also show that. And also, apart from the FPGA-based experiments to test chips, it also shows that a real user-level program can induce bit flips in a real DRAM chip on an Intel system when RowHammer cannot induce those bit flips. So by pressing a row, which will become clear, you actually induce these bit flips. And it proposes 4 different solutions to RowPress. I'm going to discuss one solution. Some of the solutions require changes to DRAM chips. That may actually be a better solution, but I'm going to discuss one solution that actually minimally changes solutions to RowHammer to also account for RowPress, but it makes them worse in terms of performance and complexity. So that's basically, things are becoming worse. Memory control needs to become more intelligent. And this is one discovery. There are more discoveries to come, in my opinion. So what is RowPress? Basically, keeping a DRAM row open for a long time causes bit flips in adjacent rows. So we actually had this observation in the 2021 micro paper, if you remember, right? A deeper look at RowHammer. But we didn't know it was a different bit flip mechanism. Meaning you keep the row open a little bit longer, you get more bit flips. And we had no idea that this was a different type of disturbance mechanism. And in this paper, we definitively show that this is a very different read disturbance mechanism because we actually keep the row open much longer also. Basically, in some cases, only one activation is enough. You activate the row, wait for a really long time, and you get bit flips in adjacent rows. This is fascinating, right? Of course, this doesn't happen under normal conditions. You need to violate the timing parameter. Basically, after 30 milliseconds, you get the bit flip. But you do get the bit flip. That's the important part. So this is a very fundamental mechanism. It's not a retention error also. That bit flip is not a retention error because we know the retention time of rows. Right? Okay, so let's take a look at what this is. Essentially, mitigations work by detecting some activation count, which is usually relatively high. What if there's another phenomenon like this, basically? So this is actually Hao Song's picture. I keep using it for everything. Of course, Hao Song borrowed it from somewhere also, but it's a good analogy. So what's the difference between RowHammer and RowPress? Essentially, instead of using a very high activation count, this was actually the RowHammer pattern that many, many people were using, which is the activate a row as frequently as possible. Activate, precharge, activate, precharge, activate, precharge as frequently as possible allowed by the DRAM standard. It leads to RowHammer bit flips, and you need to do some number of activations to induce bit flips. RowPress says, don't do that as frequently as possible. Actually, keep the row open for a long time. it turns out keeping the row open a long time induces disturbance that is much more effective than activating it as frequently as possible. And in this case, for example, in this particular example from a real chip, you need only 5,000 activations to induce the bit flips, as opposed to 47,000. Which means that you need, in order to, if your mechanism again is detecting, let's say, even 10,000 activations to refresh the adjacent rows, for example, you will get bit flips with this sort of access pattern. Okay, I already said the only one activation, right? And we tested this on a lot of chips using our infrastructure again. That's the beauty of this infrastructure. It enables you to discover things. All manufacturers are vulnerable that we tested. And it amplifies DRAM is vulnerable to read disturbance for all manufacturers, and it has a different underlying error mechanism. So let's take a look at both of these. So these are summary results. This is the first figure in the paper. And you can see that on the x-axis, you have the aggressor row on time, which is T-agon. And there are a lot of results in the paper that I'm not going to show you, but you can look at the paper. This is one of the required papers, I think, in the next homework. So 36 nanoseconds is essentially RowHammer. As you keep the row active longer, 7.8 microseconds, for example, you get an order of magnitude reduction, maybe more than an order of magnitude reduction in the bit flips, as you can see. This is a distribution of all the DRAM chips, an AC min is activation count, minimum activation count to induce a bit flip. And this is double-sided versus single-sided. So there's also interesting things about double-sided, single-sided that we're not going to talk about right now. But basically, as you keep the row active longer, 7.8 microseconds is actually allowed by the DRAM standard. 70.2 microseconds is also allowed by the DRAM standard if you actually pull in refreshes. And there's a mechanism called refresh scheduling in DRAM, and that gives you some elasticity in when you can schedule the refreshes. If you do that, it allows you to actually keep the row open for more than around 70.2 microseconds. And you can see that there's almost an order of magnitude reduction, right? So basically, that's the standards. You can do this within the standards. If you violate the standards, keep the row active for 30 milliseconds, you get bit flips with one activation or two activations, whatever. But one activation is right here, as you can see. And that's true for all manufacturers over here, as you can see. So the curve is very similar across all manufacturers. This is very interesting, right? It's a beautiful curve in that sense. Does that sound interesting? Okay, so that's basically the idea. And with this, now you actually can get to very small numbers of activations to induce a bit flip. So this was our original paper in 2013. This was the revisiting RowHammer paper. And this is row press. So you get a huge reduction in the number of activations to induce a bit flip. So essentially, these are results from Hao Song's paper on DDR4. These are DDR4 chips that we tested. You get a bit flip after 380 activations. A lot of real applications can do that, actually. Just again, to give you a perspective, within a refresh interval, you can do 1.4 million activations or so. 380 is nothing. You get bank conflicts, you get easily to 380. And more recently, Ataberk repeated some of these row press studies on HBM2, and you get bit flips after 335 activations. And this was with T-agon equals 7.8 or 7. This should be 7.8 actually. I'm going to fix that. Okay, I'm not going to fix that now. Please remind me to fix it. That should be 7.8, not 7.2. Yeah. If you actually keep the aggressor row active 70.2 microseconds, which is also allowed by the standard, now the activation count to induce a bit flip is 51. Now we're getting closer to 1, as you can see. And for HBM, it's 123. So this is a bit scary in that sense. And these are FPGA results. The question is, of course, can you do this on a real system? On a real system, it's much harder. But before we go into the real system, in the paper, we have a lot of results that show that this is different from RowHammer, because row press gets worse as temperature increases. And again, we didn't know exactly why, but later works in the device level that got inspired from this work described why this happens as temperature increases, because it's really a leakage mechanism. It's called the passing gate effect, actually, in some this literature. And it's also different from RowHammer because it affects different cells compared to RowHammer. So there's a set of cells that are vulnerable to RowHammer, There's a set of cells that are vulnerable to row press, and there's the intersection that are vulnerable to both. And the intersection is extremely small, like 0.02%. And the RowHammer vulnerable cells are a lot, row press vulnerable cells are a lot. So the Venn diagram, the intersection is almost non-overlapping in the end. So and this definitely shows that these are actually different effects. And also retention failures, but hopefully it's clear that these are very different from retention failures. And there's also more results in the paper that shows that row press behaves differently as access pattern and temperature changes. So clearly we said RowHammer has a very difficult to model and understand relationship between temperature and the vulnerability of the cell. Whereas row press, it's very clear that as temperature increases, this becomes worse. And also a double-sided RowHammer is always the worst RowHammer pattern compared to a single-sided RowHammer. But it turns out row press, sometimes single-sided row press is worse than double-sided row press, and this pattern changes. And again, later, we didn't understand why exactly this was the case. So if you think about it, what we're doing is we're testing the DRAM chips, and we're trying to understand under what conditions they fail. We don't have visibility to the device level, and that's not our expertise. And I don't want to claim ever that that's my expertise because I don't know the device level as much. But there are other people in the world who have developed the expertise at that level. They read our paper, and they basically tried to understand why this is happening at the device level. And they wrote a paper that explains a lot of these things 1 year later after our publication. So that's actually fascinating, I think. You do a discovery at the system level, and later people can explain it at the lower level, but they didn't know beforehand. Yes? That's true, neighboring rows, but different cells. So because neighboring rows have, let's say, 8K cells, right? RowHammer affects a few, I don't want to say a few, but let's say 100 of these cells. Row press affects maybe 200 of those cells, and the overlap is maybe 1 or 2. That's the order of magnitude, kind of. Yeah. So you're not affecting all of the cells in the same row, basically. Not all cells fail. Yeah. Yeah. Okay, so that's basically from a device level, from this FPGA perspective, yes, you need to keep the row open. Yeah, and if you actually close the row after every activation, you minimize the amount of time and you're less vulnerable. That's true. But the problem is you don't exploit the locality in the row buffer if you don't have some sort of open row policy. Yeah. That's a great question, basically. It's good for you to read the paper. Maybe you can think about it. There are some cases that we don't know exactly. There are some cases maybe, I think there's some case in the paper. If you keep the row closed for a long time, sometimes you get bit flips also. But I'll defer that right now. So there are some things we don't know fully yet. Yes. No, okay, that's a good question. I believe so. If you keep hammering it, you increase the temperature at some point, yes. Especially this becomes a bigger problem if you're 3D stacked, because you keep hammering, you're doing a lot of activations. But I don't think we measured that. Did we measure it? Okay, take a look. Yeah, yeah. I mean, we looked at the effect of temperature on the RowHammer and row press bit flips if you keep the temperature constant. But how much effect does hammering have on temperature? I'm not sure. It becomes a bigger problem on HBM. In DDR4, it's very hard to increase temperature, actually. But HBM, because you're 3D stacked at the memory layers, the heat cannot escape anywhere, right? And cooling may not kick in as quickly. So there could be some temperature increase. That's a good question. Maybe you can study that with the infrastructure. 1 degree Celsius? Okay, so we measured it. Okay, HBM2. Yeah, this may become worse with more tighter integration, of course. Okay. Okay, so we did a real system demonstration. So of course, once you discover something like this, the question to ask is, can you actually induce this with a user level program in a real system? And Hao Song was able to do that with help from other people also, like Ataberk. But basically, the idea is, can we write a proof of concept program that keeps the DRAM row open for a longer period by keeping on accessing different cache blocks in the row, assuming there's some sort of open row policy that's employed in a commercial memory controller. And it turns out a lot of commercial memory controllers have some sort of open row policy. They don't close the row immediately. They wait for some accesses to the row. And sometimes they actually have prediction mechanisms. They try to predict if a row is going to be accessed and keep the row open for longer. They don't keep it open indefinitely. At some point, because of power reasons, they actually close the row, because keeping the row open actually consumes more power than closing the row. But we were able to induce bit flips. Basically, this is a proof of concept program. These days, in order to induce a bit flip in a vulnerable chip, you need to jump through a lot of hooks, a lot of hoops, actually. So this is actually a very small example part of the program. You need to synchronize with the refreshes. So you're going to read some papers and the security attacks. So security attacks are actually hard, but this is the gist of the program. You keep accessing the two aggressor rows in a double-sided RowHammer or row press, and you basically change the number of cache blocks accessed for a given aggressor row. Essentially, for a given aggressor row, you keep accessing the first cache block, next cache block, third cache block, fourth cache block, etc., and you vary that parameter, n, let's say. And if the memory controller keeps the row active, then it should keep the row open for a longer time. And that's what we discovered, essentially. Basically, on this real system, we showed that we cannot induce RowHammer bit flips, regardless of however hard we tried. But we were able to induce row press bit flips, assuming we accessed, for example, 32 rows, 32 cache blocks in a row, and 48 and 64. So we weren't able to induce bit flips over here. But later, actually, we actually updated these results. So the updated version of the paper has more bit flips. Maybe earlier also, I don't remember right now. So you can actually improve the attack, because this is a real system attack, and you need to deal with a lot of things that are happening on the processor as well as the memory side to induce the bit flip. But this is essentially showing that you can induce a bit flip in a real system. And later, other people replicated our results. I'm going to mention some of those. From Amazon also, for example, people have replicated. So the next question is, of course, how do you mitigate this, right? So there could be multiple approaches. One of the approaches that we propose is to adapt existing RowHammer solutions. Whatever RowHammer solution you have, you can adapt it with two principles. One is, so this is what things look like, basically. There's some curve, not linear, but this sort of curve, and you can find in this paper. As row open time increases, your activation count to induce a bit flip reduces. Okay, you figure out that curve by testing, of course. You test the DRAM chips, right? And at some point you say, I'm going to limit the maximum row open time, because if AC min is like 50, I'm not able to handle that in an efficient way. So I'm going to deal with AC mins of, I don't know, 500, 1000, whatever that is. So you get a cut at row buffer locality you're exploiting. But hopefully, most programs don't have huge locality like that. Now, the question is, of course, there are some programs where locality is huge. Then you lose performance on those programs, right? A little bit. But this is a trade-off, basically. How aggressive your solution should be versus how much locality you lose. So you limit the maximum row open time. And then you configure the RowHammer mitigation to account for the reduction that happens in AC min. So this is the original RowHammer mitigation configured for some AC min based on testing. And you look at what happens at maximum row open time with to the AC min, because you keep testing the chip, and you change the adapted mitigation strength. That's the idea. For example, you refresh rows more frequently, or you throttle rows earlier. That's the idea, basically. Any RowHammer mitigation can be adapted this way by following these principles. Hopefully that makes sense, right? That's the good news. The bad news, of course, once you do this, you're going to lose some performance. There are two cases where you will lose performance. One is by limiting the maximum row open time, you're going to lose performance on workloads that actually keep accessing a row sequentially. The second is you adapted the RowHammer mitigation to include row press mitigation also, and the mitigation is now more aggressive, so it's going to take actions more aggressively. As a result, you're going to lose performance because of that also. And we check how much performance you lose. We adapt graphene. Graphene is one work. It's actually a lot of the papers cite that. You can take a look at it also. It's a way of keeping track of the activation counts in a deterministic way for different rows. It takes advantage of an algorithm called Mizragui's algorithm. And if you adapt that, you basically lose some performance on average, not that bad, but maximum performance losses are large, as you can see. And if you actually have maybe other workloads that are much more intensive, you lose even more performance. Yes. Okay.
So, given that we reduce the maximum time on rows, maximum time on rows can count. So, and given that we have access to that row,
yeah.
So, it will result in hammering. So, the solution for rows will become a it will cause row hammering.
Yeah, that's so I see what you mean. Basically, you can have more. So what you're saying is you can have more activations. I mean, that's true compared to keeping the row open longer. You'll have more activations. But again, the program can have more activations to begin with, right? So you have an activation. If you think about it, an attacker program can have 1.4 million activations. You cannot have more than that. If you keep the row open longer, the number of activations you're going to have will be lower than 1.4 million. You see what I mean? There's a budget that you cannot exceed. And if you really want to have that budget, which is not the optimal attack, as RowPress paper has shown, you can use that budget if you want. So by doing this, we're not really making RowHammer worse. Makes sense, right? Yeah. Okay. Okay, so you can see the mitigations, but Para's performance overhead increases significantly, as you can see. So there's low additional performance overhead on average, but it's still not comfortable, basically. Meaning, as you keep finding these disturbance mechanisms or bit flip mechanisms, you're going to be less and less comfortable because your performance overhead to mitigate them will increase and increase. Okay, so this is a summary of the paper. I will not go through the summary. But this paper actually won the Distinguished Artifact Award at ISCA, which is not easy to get. There's an artifact evaluation that happens and independent people evaluate. Assuming they do a good job, they give these awards, and not all awards are deserved, but in this case, it was a very well-deserved award, in my opinion, because a lot of people actually were able to easily replicate these results, and it enabled a lot of research, as I will show you, in industry and academia. So that's the paper. It was also selected as a top pick by IEEE Micro. So there's a shorter version of it that we wrote later with updated results, actually. If you're interested, you can take a look at it. I didn't have a screenshot of that. So I presented this paper also last week. Was it last week? I cannot keep track of time these days. I keep traveling. But essentially last week at the top picks in hardware embedded security. So I discussed the impact. So I think it's good to think about this because there's more to come in this area. So the major contribution of this work is discovery, analysis, and demonstration of a new DRAM bit flip and read disturbance phenomenon or vulnerability, whatever you want to call it, and new solutions for it. And this is basically the summary. You basically go to this blue bar with this sort of phenomenon. It greatly reduces the number of activations to induce a bit flip. And this is the summary of the impact. Industry actually already acknowledged that RowPress should be mitigated. You can watch the DRAM sec, for example. But Samsung, I think, has papers. Maybe I have some slides on this. Microsoft and Rambus reports. And JEDEC is also discussing how to mitigate this internally. It's enabled many new read disturbance mitigation techniques. There are actually papers to solve RowPress. It's enabled work on worst-case bit flip access patterns, because now you have another dimension, right? It's not just how frequently you activate and how many rows you activate. It's also how long you keep a row active. And now, what is the worst-case access pattern becomes a good question, right? Because you have three dimensions: how frequently you activate something, how long you keep it open, and which rows you activate. Maybe you activate one neighboring row for longer, another neighboring row shorter. How much? So there's a huge space of different access patterns right now. That's very, very difficult to figure out exactly. So you cannot exhaustively test the space easily. So this is an open question right now. What is the worst access pattern to induce bit flips in DRAM? It was less open before. So right now, especially like if you're doing this from a CPU perspective, you're writing a program, that's also very difficult. What is the worst case is very difficult to do. But even in an FPGA, you have complete control as in terms of how long you keep a row open, which rows you activate, etc. Even then, we don't know what's the worst access pattern. How do you combine RowHammer and RowPress, for example? So we have a paper on that, but that's not the worst case. But we just show that it's worse than what was previously shown. It enabled new circuit and device level understanding. I think this is fascinating. And this is actually, in my opinion, a very, very fundamental advancement because RowPress was not modeled or documented before this paper. It enabled more powerful DRAM bit flip attacks at the system level. There was also extensive media coverage and people debated things a lot. So this is the top pick paper. Okay, I have a link to the top pick paper. This is a shorter version of the paper with updated results if you're interested. And there are people who talk about RowPress. For example, this is an innovator at Rambus, who's also an academic. He's written a lot of nice papers actually on different topics, including RowHammer mitigation. They actually discussed RowPress in this DRAM security workshop. If you're interested, you can take a look at the YouTube video of the workshop that we have. Samsung basically acknowledged the issue and they said they're implementing measures, but we don't know what they're implementing. I hope they're not implementing the paper that they wrote in 2023. That would be bad, but I don't think they're implementing that. That's good. And also there's more discussion to educate the community, etc. Yeah. So in this place, there's a lot of discussion on RowPress, for example. There's RowPress and HBM. So the same study where we studied HBM chips, we actually show the effect of RowPress. So RowPress is actually worse on HBM also, as expected. And I've already shown you these values that I will not repeat again. So this is basically, if you can combine RowHammer and RowPress in different ways, you can actually induce bit flips earlier and worse. And this paper covers some of that space. How do you combine RowPress and RowHammer across different rows in different ways? Like how long do you keep one row open? Which row do you activate when? So there's also the when aspect. So it's actually a very complicated space to figure out what is the worst access pattern to DRAM today. RowPress affects processing in memory. This is Ismail's work over there. You can ask him. Maybe he's going to present it at some point. Maybe tomorrow. Let's see. Since we're not going to finish, I think, the entire slides, we may describe this tomorrow. So you've seen processing using memory. You've seen RowHammer and RowPress. And a natural question to ask, and I've gotten this question many times actually before Ismail started doing this work also, and I never had an answer. My answer was basically, you should solve the RowHammer problem separately. But Ismail showed that RowPress and RowHammer actually affect processing using memory very badly. And I'll leave it at that so that he can give you how badly. But this is another thing that you can do with this sort of infrastructure, right? That's why I'm proud of the infrastructure that we built. And even though it's taken a lot of time to develop many different types of infrastructure, we should do more of this to figure out more things. Do you agree, Ismail? Okay, he agrees because he's been discovering a lot of things. Okay, so there's also a work in like security community. RowPress is relatively new, right? 2023, but immediately security community actually picked up on it also. This work from Daniel Grus's group showed that you can actually do a full RowPress attack, again, combining RowHammer as well on a real system. So they kind of validated our results, real system results. And there's also some other work this year that basically show that you can reduce accuracy in deep neural networks by using, again, RowPress that targets certain bits in weights. So it's great that people are actually building up and building up the pressure on doing something better on the memory side. And this is the PhD thesis of Jonas, who did some of the RowPress work, and it's a nice thesis if you want to look at it. There's more work. This work by Kave's group here actually built some infrastructure to analyze how long a row is open, for example, in real systems. They were able to reproduce RowPress bit flips, but they also showed that many existing, at least the existing memory controllers that they tested, do not keep the row open as much. So there's a lot more room actually to keep the row open. I mean, they don't quite understand why it's not kept open, but they have an infrastructure to measure that, which is good. And there's some RowPress mitigation works that are similar, that do some work, but we're not going to cover that now. And these are the device level papers that came up. This is actually the fascinating parts, in my opinion. These folks from Shanghai Jiaotong University read our papers, and they basically, independently of us completely, they asked us some questions actually, but they independently of us, they tried to understand why this is happening, and they modeled at the device level, and they published these works that, in my opinion, are seminal at the device conferences to describe why this is happening. Okay, this is Hao Song's more recent work. We actually been trying to understand some disparities between those device level works and what we observed at the system level. And this actually is a paper that describes what are the disparities. Device level works that are published predict something, but at the system level, we're seeing something else. And again, I'm not going to describe what those exactly are. For example, bit flip prediction. We expect the bit flip prediction to be from 1 to 0 based on the device level modeling, but we see 0 to 1 bit flips. Why? We don't know, basically. So there's some inconsistencies that exist based on our device level understanding and the system level testing. The question is, why do those exist, and can we actually bridge the gap? So this is actually a fascinating area. You can bridge the gap between device level and system level understanding, and we're working on that right now. Okay, so basically there's more to come. WordPress actually inspired many studies and other discoveries in DRAM, and these are some of the things that you can take a look at if you're interested. These are the references that I mentioned, and maybe some other references that I didn't mention. And the academic impact of WordPress grows also. So I think this sort of discovery will continue to inspire more solutions, attacks, and vulnerability discoveries. So I think we should be looking more into it. This is the summary paper, if you're interested. So there's more to come. Now let me give you a small inspiration of what else is to come. So we need to understand bit flips more, and I think we need to understand hardware errors in general. There are many effects on bit flips that still need to be rigorously examined. Aging, for example, is something that we have been working on for multiple years, but we need to figure out exactly what's going on. Maybe someone brave here will discover things, because aging is a bit scary in my opinion, because you take some machine, put it somewhere, and it stays there forever. It ages. It ages in multiple ways, right? It may age because of environmental conditions. It's exposed to a lot of heat or cold. That's a different kind of aging. These are different aging mechanisms, right? It gets exposed to a lot of current that may happen for whatever reason, right? It gets exposed to different workloads. They also age things, right? So all of these aging affects DRAM, and how do they affect these bit flip mechanisms, right? So ideally, we would like to use the cutting edge technology, the most efficient technology, and use it under many different conditions in space, for example. Today, people don't use cutting edge technology in space because they know that it's not reliable. Right? They actually use very old technology that they validate. And as a result, you are limited in what you can do when you actually send some computer into space. Right? So basically, aging is really important, I think, for us to understand. We have not understood it yet. That's the unfortunate part. And this requires even more infrastructure work and a lot more experiments to do. Environmental conditions, voltage, temperature, there's more to examine. We can examine some temperature range. What about much lower temperatures, right? People are thinking about building quantum computers, for example. That low temperatures. What happens to memory at that temperature? What happens to memory at high temperatures? Even memory access patterns, as I said, we don't quite understand what are the worst memory access patterns. And also memory control and system design decisions. How do these really impact these bit flips? So there's a huge space over here, as you can see, to still examine more. And some of them are not even examined much. And also there's the other direction, which is how do you solve these, right? And these are, again, synergistic, because once you understand, you can solve better. But again, hardware errors are many. There's also how do we solve these such that if we discover something in the field, can we patch the hardware, right? And I think going forward, we really need much more programmable memory controllers so that we can patch them in the field. This opens up some other issues, of course. If you have a programmable controller, what if someone malicious programs it, right? It's good to think about that as well, right? How do you ensure that some malicious attack doesn't happen because you added some reconfigurability, patchability, or programmability? Like people have done microcode injection attacks, for example, because microcode can be updated in the field, right? So it's good to think about that. This is before. Right now, actually, microcode is relatively secure, but unless somebody forgets something. Okay. So I'm going to talk more about this, but there's more in the papers. This is one of the most recent papers that we have written on the topic. It still doesn't cover a lot of research that happened in 2023 and beyond. And we've always argued for better communication between DRAM and controller. There's another paper Minesh wrote that talks about how to have better transparency between the DRAM chip and the memory controller, such that you can design, for example, much better error correcting code mechanisms. And again, I'm not going to talk about it, but you can read it. We already talked about better partitioning of work. There are more intelligent controllers that we have designed. Abacus, which Ataberk designed. It's at Unix Security last year. Maybe he will present at some point, but we don't have time to talk about. But there are insights in these papers. For example, here the goal was to have very low overhead mitigation, and Ataberk keeps track of activation counters for a given bank, all banks in an aggregated manner. You can read the paper for more detail, but this takes advantage of the access patterns to memory for that happens in most programs. This is Nisa's work. Where did Nisa go? Okay, she's in the back. Comet. This is also a work that essentially uses a particular algorithm, count-min-sketch algorithm, to design efficient solution to row tracking using hash-based counters. And she can tell you more about it. Maybe she will present it sometime. It could be tomorrow. Let's see. So there are a lot of innovative solutions people come up with. They all have upsides. They also have downsides, unfortunately. There's no perfect solution, basically, we have for RowHammer at this point. But we are advancing the understanding. What's very clear is you have to have an intelligent memory controller. And these solutions, these ideas have actually different types of intelligence embedded in the memory controller. So there's more to actually do in this area. And I don't believe that a solution, a perfect solution, will exist actually. It needs to be a combination of solutions in the end, because it's very difficult to solve this problem, at least at very low thresholds of activation counts. Okay, there's more solutions like that take advantage of the spatial variation, which I'm not going to talk about. And this is another solution that builds on RowHammer. It turns out if you have RowHammer, or if you have even very aggressive refresh, selective refresh, reactive refresh, like para, your RowHammer mitigation may be perfectly secure. Assume that you've configured it right under all conditions, which is a difficult thing to begin with. But assume that you've done all of that. It's secure perfectly. You don't get bit flips. But the configuration leads to a denial of service attack, meaning a program that would normally cause a bit flip cannot cause a bit flip anymore, but it's triggering so many of these mitigations that other programs cannot access memory as much. So it's very similar to memory performance attacks. It's a different kind of memory performance attack. And this paper discusses how you actually throttle suspect threads. So you basically figure out which threads are causing RowHammer induced denial of service, or RowHammer prevention mechanism, RowHammer mitigation mechanism induced denial of service, and tries to throttle that thread. And eventually, you should inform the operating system saying that this thread is doing something not so good. So do some analysis on it or something like that. Basically, that's the idea. So there are some other ideas in this paper, but this tries to solve the denial of service problem that comes up with solutions that are otherwise completely secure, meaning bit flip free. Okay, and Nisa did another work over here that showed that you can actually have these RowHammer defenses can cause side channels or covert channels, and you can use the information because some thread is inducing RowHammer mitigation actions. You can basically encode information to communicate between two, let's say, cooperating malicious threads and side channels. So maybe she'll also describe this. So your mitigation mechanisms may be perfectly secure, essentially, but they actually cause other problems. They may turn a bit flip into a side channel or covert channel. And these are very difficult to mitigate. Like denial of service is also hard to mitigate, but side channels are even harder to mitigate, in my opinion, because if you want to mitigate all the side channels, it's very difficult, basically. But maybe Nisa will talk about that. Okay. And GRICs also has a lot of other things that I'm not going to talk about right now. But there's more to come, essentially. Let me give you a couple of other things. So there's still actually a whole lot we do not know about DRAM today. This is really fascinating. After 60 years, we're learning a lot. So this is one of the aging studies that we did with GRI. Essentially, if you keep hammering a DRAM chip 68 days, don't ask me why 68, ask GRI. This is actually taking a lot of resource on our infrastructure. So 68 is a good number, I guess. It could be 168. Then you need to do testing for longer. But basically, this paper showed that aging can lead to redisturbance bit flips at smaller hammer counts. This is one example, aging. But there's more that needs to be done to understand the aging. And there are different kinds of aging, right? This is one kind of aging, I would say. There are different kinds of aging under different conditions. And we really need to understand this, in my opinion. Otherwise, we really don't know whether we can rely on these chips under different conditions, right? So that's from this paper. This picture is from Giray's HPCA paper. Okay, what are the other discoveries that happened? So this is actually fascinating. It's very similar to variable retention time. But again, underlying reasons we don't know of this. Nothing is documented. Essentially, the idea is this paper shows that, this is Ataberk's work, with the read disturbance threshold, or the number of activations to induce a bit flip of a row, changes randomly and unpredictably over time. This is very similar to variable retention time phenomenon that you've seen, except it happens for read disturbance threshold also. And you remember how much headache variable retention time caused us. This caused even more headache, because now how do you configure your RowHammer defense? Right? You have this variable read disturbance that affects both RowHammer and RowPress. How do you configure the defense? Because you test DRAM and you figure out that read disturbance threshold is X, and then 10 days later it becomes X divided by 10. Let's say. It's not linear. I just made up the X divided by 10, but it could. You cannot rule that out, basically. Again, in the field, this could be a vulnerable chip, right? So there's no good solution to this also, even though this paper has a lot of analysis. After this paper was published, we actually did a lot more testing. And the problem is even worse than what this paper shows. So Ataberk is working on other works that actually show that this is becoming much worse. More recently, Ismail, again, in the back, showed that. Do people know you? Okay, he's the big guy over here. Yeah, he's a traveling salesman in the world. He's traveling to many conferences and selling these errors for a good reason, of course. But in this work, Ismail showed that there's another phenomenon in DRAM, which we didn't want to call column hammer, but we called it column disturb. That is not a big deal today, as far as we know, although the jury is still out. Maybe there's more testing that will show that this may be a big deal. We don't know yet, but at least this paper shows that whenever you activate a row, you actually induce disturbance in the bit lines, right? All of the bit lines, 8,000 bit lines that are connected to this row. And that disturbance that happens on bit lines essentially affects the cells, all of the cells that are connected to the bit lines, including in this subarray, as well as the subarray that are connected to this subarray, meaning all of the 3,000 rows are affected because of column disturb. This effect is not as bad as RowHammer today, but it's getting worse over time, meaning as the cell sizes and distance of the cells become smaller and smaller, we see that this effect is becoming worse. And Ismail can talk about that in more detail. There are real bit flips that are possible to induce in a very, very small fraction of chips within a refresh interval. So hopefully you're going to talk about that. I'm going to leave that there. So this is also another read disturbance mechanism that was not documented at all before. We have some hypotheses as to why this may be happening, but there needs to be more device level work to really understand and explain why this is happening exactly. And this is the other work that I mentioned that Ismail is also going to talk about. Ismail is going to give a lecture, as you can see, soon about these things. The read disturbance becomes much worse with processing using DRAM. And this is something important because we definitely want to do processing in memory or processing using memory specifically. And we really want to understand how reliable it is, right? We've already given you some examples, and there is more work that needs to be done in this area. And if read disturbance actually makes it much worse, how do you make it reliable, right? Okay. So we're going to talk about emerging memory technologies at some point. I don't know, maybe tomorrow, maybe next week. But emerging memory technologies actually also need intelligent controllers. So we're going to talk about phase change memory, for example, which is a fascinating memory technology that I have worked on for many years. But it turns out these technologies are also vulnerable to different types of problems. For example, phase change memory has an endurance problem. Whenever you write to a cell, you degrade contacts that are around the cell because you actually induce very high temperatures to write to a cell in this particular case. And if you keep writing to a cell many times, at some point contacts degrade and you cannot even read from the cell. You cannot access the cell, essentially. This is called a wear out problem. The cell wears out as you keep writing to it. It's not a disturbance problem. It's really wear out. The cell wears out. And this number is very small. Like you can write only 10 to the 6 times to a cell, or maybe 10 to the 8 or 10 to the 9. Still, these are very small numbers, right? Because a processor can issue a lot of writes to a memory. So basically, the question is, how do you handle these things? And it turns out handling these things, it requires an intelligent controller to figure out how many writes you're doing to a cell and remapping rows to other places, for example, if you actually exhausted the write budget for a given row. So that's an intelligent controller immediately. And flash memory actually has these intelligent controllers already because it has a very similar problem, much worse than phase change memory. Because in some flash memory, especially in very densely packed flash memory, the number of writes you need to do to a cell to induce a bit flip is around 100. It's a bit crazy, right? You do 100 writes and you cannot do any more writes into the cell. Right? So you need to really have an intelligent controller to solve these issues. So no memory technology is immune to these effects, basically. That's why I'm telling you this. The takeaway is there's a lot of evidence that no memory technology is immune. Some memory technologies are much worse because they have this endurance problem. The DRAM is actually not that bad because it doesn't have an endurance problem. You can keep writing to DRAM and it'll still work. As far as we know, this may actually become worse with smaller technology nodes. The other issue is a lot of these technologies, like phase change memory, they're emerging memory technologies, meaning they're not in full production manufacturing. And as a result, they haven't scaled down to the dimensions that DRAM or flash have scaled down to. And as a result, it's very hard to claim that they're not going to be vulnerable when they scale to very small dimensions. Okay, so all memory is fascinating and all memory has problems, basically. That's why we should keep building this sort of labs and investigating what's going on. And we actually help a lot of people in the world to jumpstart their labs, and this sort of infrastructure, like the DRAM vendor infrastructure, has been used in many different places in the world, including Korea, US, China, etc. Japan. Oh yeah, Japan. I forgot Japan. Yeah. Ismail travels to Japan and Korea all the time, so he knows Japan better than me. You did go to Japan twice this year, right? So I'm not wrong. Yeah, there you go, for a conference. Yeah. Okay, so I would say that, so a little bit of things I learned actually based on what we have seen. Basically, we developed this infrastructure, but the infrastructure was actually rejected multiple times. So it's good for researchers to follow their passion. We actually got some pushback. I'm going to show you that. I don't know about today. Let's see. But probably tomorrow, like how RowHammer was initially received by their users. It was rejected once, even though we actually demonstrated using real chips, right? And people said interesting things. We could have given up, of course, but you should not give up, basically. You should follow your passion. If there's something big that you're doing, and we believe that we're doing something big. And actually, I think a lot of people really understand that these days. Hopefully, they'll be smart enough not to reject real results. That's also interesting. But you should follow your passion, regardless of whatever other people think. And actually, people who have followed their passion have changed the world, right? And I think what's really interesting in this case is you really need to build infrastructure. You should not shy away from that. This infrastructure is not easy to build, but you got to put work. You got to put the hard work to actually build that infrastructure. And there's actually a very good infrastructure in place, but there needs to be more done in this area, which requires a lot of hard work, of course. But I think most important thing is be resilient, right? You've seen the Richard Hamming paper, and I agree with him that people need to be resilient in terms of if you want to innovate, there will always be naysayers against you. Everybody has seen this, right? Whatever domain you want to innovate in, there will always be people who want to keep business as usual. Okay, just to give you an idea, RowHammer has exploded even more in recent years. There are works in major conferences. You can see that in reliability physics also, but also high-level conferences. You have RowHammer works. There's a DRAMsec workshop, which is actually mostly RowHammer. There are serious changes in standards. There are PhD theses. There are more RowHammer works. There are even SOSP papers, like operating systems conferences. One of the SOSP papers actually introduced subarray level isolation, basically. If you cannot protect against RowHammer, isolate things across different subarrays, for example. This is a pure operating system level work, which works under some cases, but it doesn't get rid of bit flips, of course, right? But it's good that people are exploring. So there are redistribution sessions in ASPLOS this year, ISCA. DRAMsec actually was very nice this year with a lot of papers and also a lot of interesting discussion in industry, and you can watch it completely online. And at Usenix Security, as I mentioned, there are 7 papers, which is also interesting. And these are actually looking at different aspects of RowHammer. And at Micro this year, there were 4 papers. Granted, 2 of them are our papers, but yeah. Okay. So future. Future is very bleak, meaning memory technology is not going to get better. This is where we're pushing the future, right? Some people who are developing AI processors or machine learning accelerators are finally waking up to the fact that memory is important. You see some of these people, as if they've discovered the world new, they write papers, memory wall in AI. I find it interesting. It's good that they're writing papers, but they should also acknowledge that this is not new, right? You can find these papers, which is interesting. And memory capacity is a big problem. Memory bandwidth is a big problem. That's good that they're discovering things. And it's going to get worse, basically. If these people are just discovering memory, they're going to discover more in memory going into the future. And they need to do something different. And hopefully something different is really changing the paradigm to be much more memory-centric. But basically, from a memory robustness perspective, DRAM is becoming less reliable and more vulnerable. And due to difficulties in DRAM scaling, other problems may also appear, or maybe going unnoticed. And discoveries like RowPress are going to be supplanted by other discoveries, in my opinion. We've already discussed read disturb errors, retention errors, but there could be more, basically. And this is actually a field of creativity also. What else could be happening in DRAM? Can I test for it? Can I discover it? Right? Can I induce it under some conditions? Under what conditions can I induce it? This is actually very interesting experimentation. In my opinion, this is true computer science, actually, because you're really discovering, you're really developing some hypotheses on a computer, and this is a scientific hypothesis, and you're trying to validate that hypothesis, right? It's a bit different from engineering a new computer. You're really studying a computer in a scientific way. So it's good to think about that. Sometimes computer scientists think it's all about algorithms and software, but this is true computer science. You're really studying the computer science. Okay, so what about other things? DRAM is vulnerable. Flash memory we're going to study. It's actually also quite vulnerable, but flash memory is a bit outside, far away from the processor, which we want to also change. So it's a little bit more protected. There are also emerging memory technologies. Unfortunately, all of them are vulnerable. All of them have different types of phenomenon like endurance, retention, read disturbance, write disturbance. So there are papers on STT-RAM, for example. We will see some of these technologies in a later lecture. Basically, there are RowHammer attacks on all of these technologies also. They call it RowHammer, but I would call it read disturbance, essentially. They essentially have read disturbance and write disturbance problems. Maybe there's some other technology that's less vulnerable to this. And actually, people are considering making DRAM 3D. And maybe if we have time, we'll also discuss this at some point in the emerging technologies potentially. And we don't know the effect of those technologies on RowHammer yet. In fact, there are device-level proposals for future DRAM, resistive DRAM also. People are looking at resistive ways of designing DRAM, and they claim they're less vulnerable to RowHammer, but that remains to be seen also. So the future is a little bit unknown. From my perspective, based on all of the studies that we've done with all types of memory technologies, it's very difficult to get rid of reliability issues, especially if you're packing so many cells in a given area, right? You need to figure out what's going wrong, and you need to actually really have an attacker's mindset, right? Attack the system. How would an attacker approach the system, basically? That's how you can design a much more robust system. If your mindset is what I'm doing is good, and I don't need to prove anything about it, then forget about it. It's not going to be robust, because an attacker will be much more motivated to actually do something than you. Okay. So I think in the end, the takeaway is intelligent memory controllers enhance robustness and enable better scaling. And I think this is a general approach that can protect all types of memories. So what is the approach that we have been taking? Again, not so formally, but I think there are 3 steps really. And these 3 steps can happen in a coordinated way and also together concurrently. And I think we need to do everything concurrently in general. But understanding is really important. Understanding means what's going on. What are the different mechanisms that lead to bit flips, for example. And we need to understand with real device testing. That's why we built up this lab. And we need to actually, once we understand, we need to develop models for it, right? And sometimes we need to develop models for it at the architectural level to do architectural studies. But sometimes we need to develop models at the device level And these are other people usually, because that's not my expertise, but there are device level studies that I pointed you to. And that modeling can help us design better devices. And this understanding is extremely important, because if you understand, you can better architect, and you can also better design test mechanisms that may operate in the field. The second thing is architecting. We really want principled architectures with robustness as a key concern, but security is an important part of robustness. And we want architectures that enable us to have good solutions, right? That's why we talked about self-managing DRAM, good partitioning of duties across the stack. Who does what? Does the memory controller dominate DRAM, or does DRAM have some responsibility also? How do we actually design these mechanisms such that things are easily upgradable, easily patchable in the field? If a DRAM manufacturer comes up with a great idea, for example, do they have to convince somebody else that's building memory controllers to actually add that great idea? Today, you have to do that because DRAM chip has no say in what it does on its own. But if we actually enable a better interface, better partitioning of duties across the stack, DRAM manufacturers can make their DRAMs much better without requiring permission, if you will, from the chip manufacturers. Right? That's why we need a better interface, basically, so that we can enable innovation on both sides. And patchability in the field is important, and hopefully this gives you, all of these lectures give you an idea, because a lot of these things are discovered on DRAM chips that are already out in the field. Right? And if we can do it, maybe some malicious attackers can do much worse. Right? Of course, they probably need to use our infrastructure to figure out what's going on. Okay, design and test is also important. Like, how do we actually design fundamentally for robustness, right? Today, chips are designed mainly for capacity. Right? Robustness is a concern, no question about that. But it's becoming harder and harder to mitigate these concerns, as you have seen. So we keep on pushing capacity, but how do we actually incorporate robustness as a first-class constraint in the design? How do we actually do testing, for example? This is actually a very difficult problem. We have multiple papers on profiling, testing DRAM chips, different types of errors, retention, RowHammer, RowPress, RowHammer plus RowPress. So testing becomes very difficult. And testing is actually the biggest cost of manufacturing a chip today, whether it's a processor chip or a DRAM chip. The biggest cost is really testing and verification. And if these key issues keep getting discovered, you need to test more and more under many different conditions. You've seen the example of RowHammer and RowPress, right? The dimensions explode the testing space in the end. So how do you do this? I think the solution is really doing more online testing. Offline, you're conservative, maybe. You do some testing as much as possible. But at some point, you go online and you keep doing testing online in the field while the system is in operation. And you have an intelligent memory controller that basically identifies things that are good or bad over time and adapts to that. I think that makes a lot of sense. And that will reduce some of the costs also of testing, but it needs to be done, again, carefully with a better interface between the memory controller and DRAM. Then the question becomes, of course, how do you support these testing mechanisms? Like, who does it? Internally, DRAM can test itself. This was actually one of our proposals with self-managing DRAM. If you have self-managing DRAM, internally, the DRAM can test different areas quickly and basically take some action. Right? If it figures out that there are some faults in some areas, it can try to disable those things, or at least inform the memory controller that it needs to do something about it. Right? So there's a lot of innovation that could be done in these areas. So the future is very bright. That's why we keep building this infrastructure. And there's more to be done in this infrastructure also. Any questions? Otherwise, I'm going to get to the bridges. So we started with bridges in this lecture, right? This was the bridge. Now, human beings have not figured out how to build bridges, sadly, across many thousands of years. This is Han, River, and Seoul. Where's Jaewoo? Jaewoo is our intern from Korea, but it was his birthday yesterday, so maybe he's drunk or something right now. Yeah. Anyway, this was a big disaster in Seoul. This is Minneapolis in 2007. This is Genoa in Italy. I think I'm correct, right? Is there someone in Italy, from Italy here? No Italians? Okay, Genoa, there you go. Okay, yeah, you have a side channel over there. And this is somewhere close to my heart, Pittsburgh. I actually went over this bridge many times. My last student at Carnegie Mellon graduated in 2021. And I was there in 2022. I saw this bridge when it was broken. It's not fun, as you can see. But these things actually still happen. And these are robustness problems. That's a beautiful view of the Frick Park over there. Yeah. Okay. Not so beautiful if you're in that bus or car, right? I don't think anybody wants to be in that thing. Okay, basically, my point is these robustness issues exist even in infrastructures like this, right? We keep building. You could argue that we should do better testing. I agree. Maybe we should have done better testing in all of these bridges. But these things happen. How do you protect against them? I think with computing infrastructure, we have a bit more freedom, right? With bridges, it's a very heavy infrastructure. In computing, I think we can be much more careful. It's a software infrastructure, so we can do a lot more. But the difficulty is computing is everywhere, right? Not like bridges. So the scale of computing, especially things that are making decisions for us potentially, is a bit more scary than bridges. I can always choose not to go over a bridge, but it's going to be very hard for people to choose whether or not a computer will make a decision for them for you in the future. Okay, so basically the takeaway is we need to design better computers, better intelligent controllers. So there's a huge opportunity in this space. And I'm giving you an opportunity from the perspective of RowHammer and also DRAM and also more broadly memory. Let me give you some final thoughts and then I'm going to let you early. So there's a lot of interesting things in RowHammer actually. So this is a slide that my colleague at Carnegie Mellon, Satya, who teaches the distributed systems course, when he heard about RowHammer, he said, oh, this is great. I mean, this is not great, but it's great because he always is looking for examples where systems can fail. And he said he immediately incorporated RowHammer into his course in 2015 or so. Yeah, it's spring 2015, as you can see over here. This is the beauty of having colleagues who update their courses. If you have a colleague who doesn't want to update their courses, that's not going to happen. But Satya is a great guy and he updates his courses. But basically, this is actually this sort of error that is undetected and happens is also known as a Byzantine failure, meaning a failure happens and you don't know that it happened. Right? You get a bit flip. Silent data corruption is another example of this, right? Essentially, RowHammer can cause silent data corruption. This is opposite of fail fast. Ideally, if you want to design a dependable system and if you cannot really avoid that you'll get an error, then you should fail fast. Meaning you either get no result and saying that I'm done, I couldn't do this, or you get an error saying that I have an error, don't trust me, right? That's what you want, assuming you couldn't correct it, right? Assuming you couldn't fix it. So the problem with Byzantine failures is erroneous can be malicious. And the only distinction between erroneous and malicious is the intent, right? Because you have an error, yes, that leads you to fail, but it could also be used for malicious purposes. And it's very difficult to detect and confine such failures. Basically, you should do all you can do to avoid them. And this is a slide that I copy and paste from the distributed system lectures. Have you studied the Byzantine generals problem? Anybody? Byzantine failures? Nobody? Yes? Okay. In which course? Exactly. Yeah, the airplanes or distributed systems, basically. Basically, the problem is it's called Byzantine failure. Okay, maybe I'll read some of this over here. I like this actually. This is a very seminal paper by Leslie Lamport, a Turing Award winner. Reliable computer systems must handle malfunctioning components that give conflicting information to different parts of the system. The situation can be expressed abstractly in terms of a group of generals of the Byzantine army. Do people know about the Byzantine army? Some history? Is it still studied in history books? Is ChatGPT aware of that? Okay, anyway, I will not go there because I'm sure ChatGPT will give some wrong answers about this. But okay, Byzantine army camped with their troops around an enemy city. Communicating only by messenger, the generals must agree upon a common battle plan. So there are many generals, and they should agree that they're going to attack a city, right, to take over a city. However, one or more of them may be traitors who will try to confuse the others. This is a malicious version of the Byzantine generals problem. The problem is to find an algorithm to ensure that the loyal generals will reach agreement. This is also known as Byzantine agreement right now, after this paper. It is shown that using only oral messages that are delivered between the generals, this problem is solvable if and only if more than 2/3 of the generals are loyal, meaning they don't lie or they're not traitors. So a single traitor can confound two loyal generals. With unforgeable written messages, the problem is solvable for any number of generals and possible traders. I'm not going to go into that. Applications of the solutions to reliable computer systems are then discussed. So it's a beautiful paper that started a whole area in Byzantine fault tolerance. And this 2/3 is a big number, basically. So you need 2/3 of the generals to be loyal so that they can actually agree on a plan. Now, traitor, forget about the traitor, right? So you have generals and you need messages to be delivered accurately. And the messages, basically, we're going to form an attack, right? We're going to attack the city in the morning at 8 a.m. If 2/3 of the messages are accurate, you're going to attack the city or not attack the city, right? Now, if someone is a traitor, they will change the message, right? So that the attack doesn't happen. Now, the traitor may not be a traitor. There could be an error, right? Somehow the message gets wrong. That's a bit flip, basically. And then you get the wrong message. Again, you're back to the same situation. So this is erroneous is the same as malicious in the end. You can replace that traitor with a flaky message delivery, right? It's the same thing, basically, in the end. Okay, so it's a beautiful paper that I would recommend. I would also say that bit flips were very well known, right? Actually, people in cryptography, I told the story in the past, in the 1990s, for example, Dan Boneh, for example, from Stanford, who's a cryptographer, they were writing papers saying, if you have fault attacks, the cryptography protocols will be broken because someone actually can take over your secret key. And people have tried to induce bit flips, and this is a very nice paper from Princeton in IEEE Security and Privacy in 2003. I read this paper long before we looked at RowHammer at all, right? And this paper induces bit flips. Well, during my graduate studies, I read this actually, but I was not working on RowHammer during that time. This paper actually showed that you could induce bit flips in memory. And if you induce these bit flips, you can take over the Java virtual machine. Basically, the sandboxes that Java virtual machine provides to different processes, you can basically get out of your virtual machine. Because programs in Java are supposed to run on a virtual machine so that they don't destroy the other part of the environment. And they become portable that way, but you can actually take over that. Okay, so how did they inject these faults? This was their method. You can see their nice lamp over here. They put you need to have a physical access to memory, and you need to heat memory up with this lamp. That's one method of heating memory up. There could be other methods, clearly. And they were able to induce a lot of errors. This is kind of expected, right? So if you heat memory up too much, you get retention errors, for example. They didn't understand the cause of the errors exactly, but what mattered to them was getting bit flips. So this paper is a beautiful paper, actually. It's very similar to the attack that Google developed in 2015 to take over the Google native client, because Google native client is kind of a virtual machine in the end. It's not Java, but it's essentially a virtual machine running Google applications. So people knew that bit flips were bad, but what RowHammer did was replace that lamp with software in a much more reliable way. Basically, you can introduce a simple exploited error using a user-level program. So that's like this analogy I like a lot, basically. This paper, even though it's very nice engineering work, it's very nice conceptually also, at some level, there was always a niche, right? Who has this sort of access to a computer to heat up? But I think your question was nice, because if you heat up using RowHammer, maybe you do some other things. But again, if you can do RowHammer, maybe you do other things. Okay, so that's why RowHammer is really important, I think. So it actually enabled a new mindset and renewed interest in hardware security attack research, because real memory chips are vulnerable in a simple and widespread manner. You don't need physical access at all. And hardware reliability and security connection became mainstream. So that's why you see many RowHammer bit flip and attacks still, even in 2025 and 2026. There's more to come, I think. The bar is higher because people meaning the DRAM manufacturers are adding solutions. Memory controller manufacturers are adding solutions. So it's much more difficult to induce these attacks in a real system. But people also are becoming creative. It's more work, but it's good to do these to show that you can actually come up with new ways of attacking systems. And there are also many RowHammer solutions that we have discussed. Maybe most importantly, this enabled a mindset shift among security researchers. So general purpose hardware is really fallible in a very widespread manner. Essentially, all DRAM chips are vulnerable. This is a big thing. Its problems are exploitable. And this mindset actually enabled researchers not just to develop RowHammer attacks, but also ask the question, okay, DRAM chip is vulnerable, but what other thing is also vulnerable? And they asked this question many, many times, and they understood the hardware's inner workings. These are actually real security researchers who had always a knack for hardware, but they didn't exactly know how the hardware worked inside. They actually studied this, and they actually discovered other attacks, like speculative execution attacks like Meltdown and Spectre, that we're not going to cover in these lectures, but these are attacks that are side channel attacks that happen because you have caches and speculative execution, and you access data that you're not supposed to access, or you access some data, exactly. You access data that you're not supposed to access. Even though this data you cannot directly access, you can figure out what data that is because it happens to come into your caches because you speculatively execute in a processor. And it turns out 2 of the groups that worked heavily on RowHammer discovered these attacks. And there's a lot of attacks like this that are being discovered and solutions to those attacks that happen. So RowHammer actually enabled a lot of other directions that are not necessarily RowHammer. Okay, let me conclude, and then we're going to start tomorrow with probably a lot of cutting-edge research sessions because I didn't finish yet. But basically, memory reliability is reducing, and reliability issues open up many vulnerabilities. These are very hard to defend against. Think Byzantine failures, basically. RowHammer is a prime example of this, and it's the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. And implications on system security and safety are really tremendous and exciting. And I think there's more to come. We're really scratching the surface. There are other attacks, I think, and other bit flip mechanisms. The bad news is RowHammer, and I say RowHammer here, but essentially these issues that lead to bit flips is getting worse. The good news is I think we have a lot more to do as researchers and also industry practitioners. They actually have a lot more to do. They will hopefully lead to much more robust systems going into the future. We're now fully aware hardware is easily fallible, and people are developing both attacks and defenses. And hopefully, we're developing new things as opposed to rehashing the old hash-based things. But we're also developing principled models, methodologies, and solutions as well, right? That's what we should strive for. Okay, I will stop here because I kept you long. But if there are any burning questions, I can take. Otherwise, we're going to start with silent data corruption logic. We're going to discuss this a little bit, and then hopefully look at some cutting-edge research tomorrow about RowHammer. So if you want to learn about what is at the cutting edge, some of the things that I introduced, you can learn tomorrow. Sounds good? Okay, I'll see you all tomorrow then.